All right, I hope everyone here is for physics. Excellent. Let's get started. Hi, my name is Jay Villanueva. I'm a technical product design director at Epic. I've been making games for over 22 years. I shipped games both big and small in that time. And I want you to know that I play all of your games. And my job at Epic is to make sure that UEFN can make games and that making those games is fun. The agenda today is we're going to have a bit of a crash course in physics, what physics is in UEFN, what you can do with it, what does gameplay look like using physics, and I want to talk about design of physics games. So why is physics important? Well, if you utilize physics as a system, you'll find that it's a new way for your players to interact. It provides delightful responses to everything that they do. It also enables emergent gameplay. And emergent gameplay is key because it'll enable you to engage your players for longer. All of this is provided by a new physics component that we've added to UEFN. It's placeable on Fortnite props. It enables all of the physics settings for you to tune and adjust your props. I'll go over each one of the settings in here in a moment. But first, crash course in physics. There will be a quiz. It will be in the form of all of your games. So I look forward to playing them. All right, Newton's first law. A body in motion stays in motion. I think a lot of people know this one, but just a quick reminder. If you have an object and you push it, I move this with a prop mover, without friction, without something to hit, it's going to continue in motion forever. You can do that in UEFN until you adjust some of the settings. One of those first settings is linear damping. Linear damping reduces an object's linear or straight line velocity over time. It simulates friction or air resistance. It acts in opposition to the direction of motion. So you can slow things down gradually, even if no other forces are acting on it. And here's a demonstration. The blue blimp has dampening of 0.2, the green one of 0.1. As you can see, the blue one begins stopping almost immediately, and the green one a short while after. So this is one way to simulate friction or air resistance. And you'll find it right there on the component. The next is angular damping, which is similar to linear, but it's for rotational movement. The taco on the left has low angular damping, and the sign on the right has high. And you'll see that it slows down and stops, while the one spins for a lot longer. All right, that was the first law. Let's talk about Newton's second law. Force equals mass times acceleration. I promise this is the only math that will be in this presentation, but I'll explain why it's key. We've all heard this, we've all seen this, so I'm going to modify the formula a little bit in a second, but force is a push or a pull. Mass is how much stuff a thing has. Acceleration is what you do to get to a velocity. You change acceleration and get to velocity over time. So I'm going to move the formula around. And the reason why is because what you want to do with your objects is you want to accelerate them. You want them moving. And I want you to know that you have two sort of knobs that you can twist to do that are easily movable, which is force. You can always change the force applied to an object, whether through some of the devices or some of the settings. You can also change the mass of the object. So just know that these are the two things that you're going to be messing with in order to get the behavior you want out of your creative props. That's why it's important. Okay. These two trash bins have the same mass, but I want to change how far they go. I want to change their acceleration. So on the component, we have an impulse on hit multiplier. If you change that multiplier, you can change the amount of force that's applied to the object. So on the left, the multiplier is default, 0.1. This is the amount of force that pickaxe will apply to physics objects. On the right is 5 times. Big difference. Same mass, but different force. Now, the other element is mass. So you can go ahead and override the mass for any object. It's auto-calculated when you populate it, but you can override it and change it. So here are two cars. One is set to a mass of 150 kilograms, and I can barely move it. I overrode the mass on the one on the right to 10. Same force from the pickaxe, send it flying. So change force, change mass. Newton's third law, for every action, there's an equal and opposite reaction. This is fun because this is what you can use in your games to create different types of interactions for players. Chain reactions, complex gameplay, add all the elements you want. So in summary, to move something, you're going to apply forces. That's going to accelerate that object, and that creates a change in velocity. All right, thanks for surviving the crash course. Now let's talk about how we actually do this in UEFN. You can physically simulate any creative prop by adding the prop to your scene, adding the Fort Physics component and configuring it like this. So I'm going to go and grab a crate. Everyone loves a crate. And then I'm going to go up and add the component Fort Physics. After that, I have all the options available to me. I will enable physical simulation. I'll override the mass. I'll override this one, I think, to 20 or so, 25. I can disable gravity. I can start it not awake. I said it's damping. I want it to slow down a little bit, but I don't want it to rotate very much. I'll leave the impulse. I also want to note that you have constraints. You can set rotation and translation constraints so that your object will only act on one axis or rotate on one axis. But I'm going to leave them off for now. And that's it. It's configured. Then all I have to do during experimental is push changes. And it looks like this. You can also do this for custom props. If you're not familiar with the workflows, I'm going to go through it, but it's very similar. You're going to import it, set up the collision for that prop. This is a key step. You're going to then create the prop out of that static mesh, add the prop, add the component, and then configure it. So in this case, I'll be importing a mesh. And then when I'm done importing, I'll open up the editor. And I want to go ahead and clear my collision. It may have come with some collision. Be sure to double check this. For this, I'm going to add simplified sphere collision. And then the details panel, I'm going to scroll all the way down to double check to see which collision I'm using. I want to make sure that I'm not using complex collision as simple on the complexity. Complex collision as simple does not simulate in physics, but every other property should work. I just go with project defaults. Then I create a prop using the editor script. Then I drag that prop in. This one was large, so I'm going to go ahead and scale it down. Then I'm going to add the component and configure it. And then I have it in my game. And it interacts with other physics props I put in my scene. So now I've got props, I've got a ball, I can start making games. But before that, I want to talk about where we are in experimental right now in physics in terms of movement and interactions. There are some limitations in experimental. Currently, the player that spawns is a physically based character using mover. It is not the same character you get in Battle Royale. This character has some movement modes. It doesn't have everything, but right now it can walk, run, sprint, jump, swim, crouch, and skydive and glide. This character is being built from mover specifically for physics to facilitate physical interactions. This character will move using physical forces. So that's key in order to actually interact with objects properly. And as far as player interaction itself during experimental, we have colliding and pushing, so you can push with the player's body. We have pickaxe, obviously as I demonstrated. In experimental, as it stands right now, hit scan weapons also affect physical objects. So this is going to be the assault rifle, the pistol, the shotgun. Projectile weapons, support for projectile weapons and explosives will be coming later. Also, devices. You'll be able to use devices to create gameplay. We've upgraded several devices, and I'll be going over those in a little bit. So let's talk about making physics gameplay. These are the devices that we have upgraded in experimental to function with physics props in one way or another. The barrier device will block them. The air vent will propel them. These devices here apply force and set velocity. So I want to point out here that there are a couple devices that are interesting. The prop mover. The prop mover can be used to animate other props. And when those props interact with physics objects, they'll push them. So you'll be able to do things like create a pinball plunger or create a spinning blender of sorts, and it'll push objects. The next one is the teleporter. We've also upgraded the teleporter to actually move physics props. So I think that counts as applying force, because if you teleport a prop into the air, it will fall. So someone go make a Rube Goldberg machine with all of these pieces. I want to see it. So I say that some of these devices apply force and some of them set velocity. So I want to go over that example and apply what we learned earlier. Applying impulse are devices such as the pinball bumper. This applies an impulse. That takes mass into account. Force equals mass times acceleration. And then other devices, such as the D-launcher. The D-launcher, you know, is a device where you can place players exactly. Well, now you can use it with physics props. And the way the D-launcher does this is by setting the velocity object. This skips the formula entirely. It ignores mass, because you're not accelerating the object. It's just saying, boom, it's going this fast now. Let me demonstrate that. So here's a pinball bumper. I have two soccer balls. The one on the left is more massive than the smaller one on the right. So I'm going to push them into those pinball bumpers, and those bumpers are going to apply the same force. So I hit the small one. Actually sends it quite far. And the larger one, same force, gets a little push. It's more massive, so the same force resulted in a smaller acceleration. Okay, here's the D launcher. Bigger mass on the left, smaller on the right. Which one's going to go further? I heard it. The same? Let's see. The same. Well done. A+. So that was devices. Let's talk about gameplay. So in experimental, you're going to focus really on where objects are to facilitate gameplay. And you're going to do this with events for the volume device. We've added two new events, on physics enter and on physics exit. Those are usable by just the event in the editor. We also added verse API as well. So on the device, on physics entered, the equivalent verse event is prop enter event. And when a prop leaves the volume, you also get on physics exit, and the verse event is prop exit event. As you can see in the signature, the creative prop is passed in that verse event. So you know which prop entered and exited the volume. Okay, so using everything we've learned, let's make a sports game. I want to make a game where I have a ball. I know how to do that. I have a goal that's going to be a volume device. And then I want to write my game logic. What I'd like to do with this ball is every time that ball gets hit and pushed into a goal, I'm going to score. I'm going to take the ball, and I'm going to teleport it out of bounds real quick, then reset the ball and let gameplay resume. So first thing I do is I need to set properties and events in my script. So I'll expose to the editor some of the things that I want. So one of them is the creative prop. I want to know the ball. And then I want to be able to track the two volumes. So I want Team A and Team B's goal. And then on begin, I want to subscribe to the overlap event, the prop enter event for each goal. And I set it to two functions. On Team A, goal enter, and on Team B, goal enter. That's what will handle all of the logic. So let's go over what happens when a ball enters a volume and gets the callback. We're going to handle the enter event, and we want to check what entered. Because in my game, I'm not just going to have soccer balls. I'm actually going to add a bunch of props. So the players, you'll see the gameplay afterwards. I always want to facilitate a lot of physics gameplay and things that are in the scene that will enter the goal. But only thing that counts are the soccer balls. So on the enter, I'm going to check if it's a ball. And we'll go over that function in a moment. If it is a ball, then I'm simply going to tell the HUD to display that the goals occurred, and then I'm going to spawn a function to reset the ball, to move it out of bounds, and then bring it back in. And in my game, I want to introduce another ball after the first score until there are 5 balls in play, because I want this game to be chaos. Okay, check if ball. Takes in a creative prop, and we're going to just create a variable that says, is this a ball or not? That way we can return it at the end of the function. And then we're going to get a tag generator. We're going to find creative objects with tag. So I put verse tags on all the balls, of all the soccer balls, so I know which is which. Then I'm going to go through each ball. So you can't compare creative props yet, but you can compare their translation. So I go through each ball, and I say, I have this ball that entered the volume. Where is it? Give me its translation. And I go through each ball, and I ask it, give me your translation. And then I check, is that translation the same as the one that entered? So if I have 5 balls in the scene, and one enters the goal, I'm going to check each one of their translations, and I say, oh, these are in the same spot. It's in the goal. So I have found the ball. However, if the prop that entered doesn't match the location of any of these soccer balls, then it's not a goal. So I say the ball is true, and I return it. Keeping the game going, resetting the ball, I just hard-coded a location where I want the ball to be, for simplicity's sake. I will hide the ball by creating a vector 3 position, and then teleporting a prop. So you can teleport physics props using verse. And you'll see it's wrapped in an if because this is failable. Then I wait 3 seconds, and then I teleport the ball back into play. And the game continues. So the final result is a game that looks like this. What happens a lot in this game is my engineers love to stuff the goal with all these extra props so you can't score. Okay, let's talk about game design. Mechanics, dynamics, aesthetics, one of my favorite subjects. The MDA framework is a paper by Robin Hunicke, Mark LeBlanc, and Robert Zubek. It's one of my favorite frameworks to apply to games. It describes a framework where you as a designer create mechanics. You create the rules of your game. And those result in dynamics and how those rules interact with each other. So mechanics, a bunch of them together create a dynamic. Then you create a bunch of dynamics and you combine them together to create the aesthetics of play. And the aesthetics is the emotional response to those dynamics interacting. So you create the rules, those rules interact together to create the dynamics, and the dynamics create the aesthetics of play. You as a designer start at the top. On one side, defining the mechanics and rules for your game. Your players, when they jump into your game, They see the aesthetics right away. They see the totality of your work. That's how they experience your game. And that's why sometimes you'll see players who will play a game and begin to deconstruct the rules. They want to see what aesthetics you've put together, or sorry, what dynamics you've put together, and then deconstruct all the way down to your rules. If you understand both sides of this as a game designer, this is a powerful framework to use. I want to talk about aesthetics real quick, just to be clear on what that means. So aesthetics, the emotional response to the game that you've built. Some of the aesthetics of play described in the paper are narrative. That's the emotionally resonant moment where your game has some drama. And it's really awesome to do in multiplayer games as well, because you're usually on voice chat, shouting and yelling at each other. Challenge. This is player self-imposed challenges, or the challenges presented by the game. The game is like an obstacle course. Can I get there? Discovery. Finding a new way to do something, or finding something new in the game. This game is uncharted territory where you explore it. Expression. Expression could be, look what I did. Game is as self-discovery. And submission. Submission is simply, I play this game every night. I like playing this game all the time. A game is a pastime. It's a game I want to engage in. So what does this mean when you're designing your physics games? Well, it's key to note that when I said emergent gameplay, the way you get there is you design the rules, not all of the gameplay. You don't design the solutions. A lot of games that don't use physics, of course, need solutions. I'll take, for example, a Tycoon game. Tycoon games currently, they have the solution pre-built in. So with physics, you want players to determine how to solve your game. And you want to treat your spaces like a puzzle. Give them the pieces, give them the tools, and then let them have fun. Let them figure out how to get to it. And you do so by putting your rules together to create different dynamics, create interactions of multiple elements, mix in devices, use action and reaction, Newton's third law. In our soccer game, I added a whole bunch of extra props. Those props interfere with shots. Players now have to take those props into account. And then I didn't imagine this initially when I just built that game, but my engineers at one point, I turned around and they had stuffed the goal full of those props. I couldn't score anymore. So now I had to run over, remove the props so I can score, while in the meantime, they were scoring on me. That's a new dynamic that came out just by changing a few rules. So encourage play through this. So a narrative response will be from a player saying, hey, wasn't it great when this happened? And if they take that story with them, they're more likely to come back and play your game. While they're engaging with your game, the challenge, they'll ask themselves, can I do this? And if they can, that's a great player experience. Again, they'll come back for more. Discovery. That's when players ask, what if we did this? And whether they succeed or fail, they did it together. And it usually results in a pretty good time. Expression. You want them to leave and go with a story that says, hey, wasn't it hilarious when we did this? And submission. I could play this for hours. Everyone here wants that. So make toys in your games. Let your players express themselves. So let's design a simple game to drive this home. My rules are, get the furniture out of the building. You'll be in an apartment. I just want you to get all the furniture out. Leave the building intact. Don't destroy it. Use everything at your disposal to move things. It's going to be a competitive game. And it might look something like this. The player could use the pickaxe to remove furniture. But eventually, they have everything at their disposal, so a chain gun makes moving out easier, right? Now, the player wasn't supposed to destroy the building, but it's their choice. You can score them on that later. Tell them to come back. But they played their way. And that's where emergence comes from. Players choose how to get there. Players know the rules, and they may break them. Everyone here who's played a physics game knows that you can break the rules. And that things never go as planned for the player. And this is where the magic happens. This is where all those aesthetics of play come up, where players will have a good time and come back to your game. Thank you very much. At this point, we have a mic up front. I'll be taking questions, and we'll go ahead and move to the Q&A.
And here we go. So, hello everybody. My name is Chris Murphy. I am a principal technical artist on the developer relations team at Epic Games. And my job is supporting Unreal Engine developers. It's kind of takes me all across the world, doing all sorts of weird projects and trying to figure out what's going on with a lot of different things. And that means that I come across a lot of like problems that I'll face again and again and again, and eventually I'll just be like, this is something I need to probably do a talk on. You know what I mean? Like, at some point I'm like, all right, I need a YouTube video to explain this so we can help everyone out collectively. And one of those topics is something I'm covering today, which is we're going to be looking at PCG not with trees. What a concept. For the record, I love that I know that we're all turbo nerds by the fact that we applaud that statement. So this is great, and I know you're all my people. So this is originally actually had a prettier version of what I'm about to demo, but ultimately I decided to kind of go with something that was closer to just, this is what I'll be making in the space of the next, apparently 15 minutes. You got to start that timer, folks. They're panicking and it's now at 1 minute. All right, chill out. So what that means is I wanted to kind of create something that would be closer to what we're actually going to make in the space of an hour. And this may not look super impressive, but hopefully it still demystifies a bunch of concepts that I think are the ones that you need to get your head around if you're going to start approaching it. And like, again, this whole city is procedural, so I can just comfortably kind of change the size of the towers and things like that. Obviously, I'm using only one data set, so I've made like the world's simplest version, but if you're like, well, you only taught me how to build a building that looks like it's out of San Francisco, I can't use this for my project, then I can't help you. So hopefully you can abstract some of that information into your own thing. The other thing that's going on here that I just want to specify is if I was to go to draw spline and I was to say to it that I want a road to run from here to here and then like up to here, and I hit accept. That's like slightly misaligned. That'll teach me. Just pretend you didn't see that and it was amazing from the get-go. There we go. This should be able to calculate intersections according to what's there. So let's go ahead and let's spin something up. I want to get this going, and I'm also going to warn everyone something that's a little awkward. I have run through this a couple of times. But somehow every time I've run through this talk, like just as a quick practice session of just building this again, I have like a 20-minute variability in how long it went for, and I have legitimately no idea why. So we'll see where we get to in today's session. All right, so let's kick this off. I'm going to right-click. I'm going to create a new PCG system. This is going to be a new PCG graph. I'm going to look at all the glorious 5.6 templates that we just added, and I'm going to straight up ignore them. And I'm going to create a new system from scratch, right? And this is going to be called PCG underscore simple roads, okay? So this is going to be the first thing that we're creating, and I want this to have something that's going to be like wrapping wherever my roads can be in the world. So that is definitely large enough. 500 units wraps it up nicely, so we're good. And with that, I'm going to open up my graph. I'm going to kick into play. So this is what we've got. We know straight out of the gate that there's a few things that we need. I need to immediately sample all of the locations that my roads could be at, right? So I'm going to right-click. I'm going to throw in some spline data. And specifically, we want to get spline data from things in the world. Now, that road class that I have kicking around is literally just a very boring road class. It's just the spline. There's nothing fancy about it, okay? So I'm going to get my spline data. It's probably a good idea for me to project it to the landscape just in case, but that's just out of safety. And now that I've got that, I'm going to I'm going to go ahead and sample it and say, I want to sample my roads, and I want to basically create, a piece along all of my roads as we go around, right? Now, this is something that can be kind of variable between projects in terms of how you want to handle it, but I'm going to say, I want to get this to be every distance here and there. 5.6 has moved graph parameters down to here, so I'm going to spin up a new graph parameter, which awkwardly doesn't quite fit on this UI. There we go. And I'm going to call this like distance increment. So this will be like how big each piece is, one after the other. Drop that guy in and plug it into distance. Okay? So what I've got now is something that's sampling it. The problem that you get if you ever do this in the world is that it looks like it's not working, but it's actually just because it's 1 centimeter wide. You can see like a single pixel there if you squint really hard. So what I almost always do right now is I throw extent modifiers after whenever I do a spline sample, just so I can like see it. And before anyone says, have you told the engineers? Yeah, it's come up and it's on the list, but we're just not there yet. The technology is just not there yet, But no, we're getting around to it. Now, if you get this issue where you're just getting one road, it's because you need to make sure that whenever you get spline data, you've told it, I want to have multiple of you. Another good idea is when I'm sampling the spline, I'm going to say fit to curve to just make sure it gets all of it. It doesn't stop within 500 units at the end. We come back here, and we've now got the early part of our road system. Okay? Now, with that in play, it's time for me to kind of move on to this next little bit. So here's the problem. If I was to get something like this, I could theoretically create a spline from that now has markers every 5 meters. And after creating a spline, I could theoretically just throw that into a spline mesh. And like that would create a road, if I can spell the word wide correctly. There we go. That would theoretically just create a road. Like I come back here, I'll turn off my debug. And that is just kind of like wrapping spline meshes around what we've got. The problem with that is like that is not good for an intersection, right? So the question here is like, how do we go ahead and work out where the intersections are? And this is what today's session is really about, is it's kind of thinking in this data in terms of not scattering stuff, but in terms of how do we like keep things as collections of data and inform them of attributes and stuff along the way. So in this situation, what I want to do is isolate all of the spots that we have intersections. And I'm going to do this in kind of a dirty way, but it will work. Whereby what I'm going to do is I'm going to say to it, I want to calculate the distance between you and the next tile, specifically between the center of you and any other tile. Okay? Now, if I set the maximum distance on this check to be the value that I had moments ago, this distance increment, which I plug into here, what that will actually do is, if I hit the preview, whenever something is 0 distance away, it will be black, and whenever anything is more than 500 units away, it will be white. You get what I mean? The problem is that while this does work, when you start getting curvature, because of how curves work, it's possible for these two pieces to be technically closer than 500 units because they're kind of like curving around. And that's kind of unfortunate. So we've got to think to ourselves, like, how do we isolate these intersections? Someone's taking really aggressive notes. All right. Anyway, so we want to try and isolate this into like separate values, right? And what I can actually do that's works is I can run what's called a modulo function. Now, a modulo function, for anyone that's unfamiliar with it, is it allows me to divide by a number, in this case, divide by 2, and then get the remainder. So in this case, if I was to divide the index by 2 and output that to a value called modulo, or modulop, modulo, if I look at the values at the end here, I can now see the modulo is going 0, 1, 0, 1, 0, 1, 0, 1, right? Because there's a remainder 0, 1, 0. So the YouTube video people are going to be very confused as to what's going on, but there is a person with a saw in the background. So anyway, what that actually lets me do is kind of get a variable that lets me get every second indice. Do you get what I mean? And because I can get every second indice, what I can then do is I can split these things up. So if I was to get that and say I want to filter the attributes, I want to filter to see if modulo is greater than 0. If it is, I want to check the distance of those values. And if it's not, I want to check the distance of those values. And let's take a quick look at what I'm actually previewing here. Notice that is now every second one that I'm checking the distance against. And if I come down to here, that's every second one that I'm checking the distance against. So if I do that, it actually lets me kind of like get that information and say to it, that I now want to get you and merge your data back together. And in theory, this will fail if things are exactly 500 units apart in certain spots, which I'm a little terrified about that intersection that I just created doing, but we'll see. But I should now be able to run an attribute filter to say, hey, if the value is less than 1, then that's going to be an intersection. And I'm going to collapse those points. Just a quick preview. Whew. Sorry, that says last. I'm like, that math worked. That's fine, cool. So that's actually now given me all of those locations. Do you see that? Because I split it into odds and evens, and then I pulled those things back together again, and that's given me intersection data. Sorry, that saw in the background is killing me. All right, so what I'm going to do next is collapse points allows you to find points within any other radius and basically say, I want to pull those together. So if I assume, don't worry about it, I'm sure we'll get Victoria on the case. Thank you. So what'll happen is if I come to here and I run collapse points, that's actually now given me an individual point at every location because it's pulled all of them together that were within that radius. Everyone still with me on that one? So the next part that I need to do is I look at these roads, and what I need to do is actually cut the roads at those intersection locations, right? So if I wanted to cut those roads, let's go all the way back to here. And what I want to do is, I'm just going to not render the spline for one moment. So we all know that if I was to, actually, give me one moment. After I collapse these, I'm going to save this out to a named reroute node, just so we can keep everything clean. I'm going to call this raw intersections. And over here, what I'm going to do is I'm going to get the spline that's coming out of here, and I'm going to run a difference node. Now, a difference node subtracts one thing from the other, basically. If I set it to binary subtraction, it just kind of obliterates them if they're ever touching. And I can see that if I was to plug this node in. By the way, it's Control-Alt-D to only preview the node that's currently selected. And you can see that that is cutting into here. And I've now got those sections quite nicely there, right? And I bring this up because if I've got that data there in that way, also, I realize I accidentally made this spline float, which is probably going to be something that betrays me later on in this project. So now I'm paranoid. If that something goes wrong later, remind me that that's the case. But I've got this difference node here. It's subtracting. Now, the problem is if I was to just plug that back into create spline, we haven't fixed anything. Notice we're still getting the intersections, because even though there's a gap between those, it's just connecting them. But here's a fun thing that we can do. Fun thing that we can do is this, is if I was to copy the current indice that we're looking at, so index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if I was to get that index and copy it over to a new value that I'm just going to call delta, okay, so this is now just the same values. You can see if I hit A on this, you can see that that's just counting down, same as the indices are. There's a nice little bit of logic where if I was to get this and then do the difference, these numbers, so that goes from 0 to 15. If I was to scroll down delta, we should see some of these missing at some location, which is very hard to visualize when I'm looking at just a whole bunch of things in a row. But I'm copying the numbers, and I'm theoretically getting rid of some of them. So if I go all the way to the bottom, 124, but 120. Notice that? So we have different numbers here between the two. Great. So here's an interesting little bit of math. If you were to subtract after removing these things, so after I've like copied the data and then removed a bunch of them, if I was to say delta minus index, that will now give me, notice that these are all delta 0, because up until this point, nothing got removed. The values are the same number. But then we get to here, and it goes to 2, which means 2 points have been removed, right? And I get to here, and 4 points have been removed. Now, why that's interesting is what I've essentially done is if we visualize that data, if I visualize that, I can, sorry, it's very, what did I touch? All right. If I visualize that data, I can see that these all have the value 2 on them. Over here, let's go to another one. The value is 0. I really should have connected that intersection, but that's fine. 6, et cetera, et cetera. So what this is actually doing is each spline, this is really going to mess me up at some point. I'm really paranoid about it. Each of these splines is basically going to have a unique identifier along it. And what's cool about that is that I can now say to it that I want to partition the data, so attribute partition, on the last variable. And while, if I'm here, I can see that I have 4 splines, because there's 4 roads that we drew in the world. Over here, I now have 12 splines that we drew into the world. Do you get what I mean? And that's because it's actually gotten each one and split them up based on whether that last number is the same. It's grouped them all together. And the cool thing of that is that if I was to connect that to my spline meshes now, what we would see is this kind of gap between them all. I didn't realize that that wasn't overlapping over here, so that'll teach me. Pull you up just a little bit. Cool. So my point is that now we've got kind of that intersection on all of these things. Do you know what I mean? So we've now got these as individual splines. So the next thing that I need to do is look at these raw intersections and work out, does this need to be a T intersection? Does this need to be a 4-way intersection? Does this need to be a stub that's like at the end of the spline itself? Do you know what I mean? So working out what that has to be is important. And how do we get that information and pass it to something like this? Sorry, time check. All right, so how we go ahead and we do that is actually not as bad as it sounds. I'm going to, after doing the partition, I'm going to create the spline again, and I'm actually going to just copy and paste this. So we're just resampling the spline. And that'll actually give me a kind of a coherent series of points that if I look at is just my spline data reconstituted on the ground here, right? But cool things that we can do. These intersections, theoretically, they want to know how many things are stuck into them to work out if they're a 4 or a T or singular. You get what I mean? Cool thing that we can do is I can filter attributes by index, and that sounds honestly borderline useless. First time I ever saw that node, I was like, why would I ever use that? But here's a cool part of that, is I can find out index 0 on every spline, which gives me this information, right? And that's the start of every spline, but I don't know if the end of the spline is 0.10 or 0.50 or 0.100, right? Cool thing that you can do, though, is you can say, hey, I want index 0, comma, and -1. And -1 will actually give me, those are lined up, it's just this thing is floating. That will actually give me the intersections going in and out of all of these points. Do you get what I mean? Like we've actually now got that information as entry points and exit points for all of these things. And if I have the entry point and exit point for all of these things, as well as that, I've got the stubs that are at the very end where we have these start and end tiles. That's really useful because I can now use that information and project it onto here to like count the things that are near me. So I'll show you what I mean by that. First off, what I'm going to do is I'm going to get my raw intersections, and I'm going to make them real big. just big enough that I know they're overlapping anything that's nearby them, because it's important to me that for what I'm about to do, and there are quick ways to do it, I'm just kind of tight for time, I'm making big intersection points, right? Now, there's a thing called a union node, whereby if I was to get this and say to it, I want to union this data and this data, what this will do is when they're overlapping, this should be basically obliterating the other points that it's now kind of over the top of. Do you know what I mean? So I'm actually getting rid of those points, but it has kept the stubs at the end of everything for me, right? And the reason that's really useful is I've now kind of found the center point of every potential cluster, including singular clusters, right? At which point what I can do is I can use the cluster node. Now the cluster node allows me to get a bunch of information, see which thing it's closest to, or centroid, and then count the number of those things and tell it which thing that it's closest to. So in this situation, I'm going to get these, which, by the way, if I hit A, are still broken into their individual splines. If I want to cluster stuff correctly, it's a good idea for me to merge all of those points together so that they're all in one giant list. And I'm going to cluster them. And if I go to here, I can see that they've all now been given a cluster ID. And if we want to visualize that, which of course we do, that now means over here, so I'm still previewing that node. Let's preview this one. Cluster 1, cluster 3, cluster 2, cluster 5. Like they've all been given a unique identifier. And if we wanted to, in the same way as we did a moment ago, like I can kind of get that information and partition it to split it up so that all of these things are now gathered by the cluster ID that they have together. So if I preview this, I can see that as a singular point. That, however, is a T-intersection. That's a T-intersection. That is a cross-intersection. Do you see what I mean? So we can actually kind of cluster all of these things together and get that information. And the fun part of this is what we can start to do is I can start to now, ahead of time, I created something. Right? I made a few level instances that are really simple. I have, they all look kind of like this, whereby it's a level instance that looks like this, whereby it's just a series of meshes, nothing fancy, and I've added a connector location to each one to say that if a road is ever going to get attached, this is where I want to stick the road. You get me? Now, I'm going to basically say, count the number of things in your intersection and pick which one of these things you want to stream. Okay? So in this situation, I've partitioned it, so I've got that count. The next thing that I'm going to do is what's called an attribute reduce, which would never have guessed had someone not shown me that. An attribute reduce looks at a collection of data, runs down that entire variable, and you can either get average, join, max, min, or sum of those variables. It's a really quick way to like iterate through a whole loop and get information. And if you think about it, if I was to go ahead and get the index, so the maximum index of these things, and I look at data set, so that before was a T-intersection, and the maximum integer is 2. Now, because index 0 is the first thing, that means it is a T-intersection. And if I was to scroll down to another one, that says 3, which means it's a 4-way intersection. Again, we're counting like programmers, so indexing 0. And what that gets me, though, is it's actually given me the count of like how many things are in that data set, and I can pull that information back into it. So if I was to like simply get that, and I was to say, hey, I want to get you and set this to be intersection size, right? Then now this has an intersection size of 0. These points will have an intersection size of 3. For the record, this is something that in future, 5.7 and onwards, talking to you YouTube people, we're eventually going to be having the data domain being used for. And there is a data domain that's been set up in 5.6, but it doesn't have some of the filters that I would like. So I'm just ignoring it and pretending that we haven't finished it yet. So I've got this information. And now all I want to do is basically say, hey, I want to filter this out depending on the size. Because if the size is greater than 0, it's a 3 or a 4, right? But if the size is less than 0, or equal to 0, then that tells me that it's a stub, right? So let's just deal with the stubs at the start. I'm going to get you, and I'm simply going to say, I want to load a PCG data asset. That's going to be my end of the road, right? At which point I'm going to copy this information. If anyone's like, dude, where did you do this from? This is something I covered in my Prague talk. So if anyone wants to see that, it's called PCG, First Steps to Advanced Development. I'm kind of just assuming people have gotten the fundamentals of PCG before coming into this section. Sorry if I've dropped you on the deep ends. But I'm going to get this, and I'm going to just say, hey, I want to copy these points to this location. And we'll spawn meshes. Spawn meshes. Cool. That's going to be an attribute. Again, this is something we've kind of done before, so I'm kind of glossing over this one. But if I come to here, we can now see the ends of each one is spawning a stub, right? The problem is the stub doesn't actually know which direction it should be facing. And the reason it doesn't know which direction it should be facing is because I've just, the line does this, and it's putting one here and one here. Fortunately, whenever you create a spline, you can get certain, attributes from it. And I can actually tell it to give me what's called the input key. The input key literally just says the first point on the spline is 0, the last point on the spline is 1, like the middle point will be 0.5. So it's kind of like it gives it a value between 0 and 1 of the length of the spline. Why that's useful is because I can say to it, hey, I'm just going to check something else before you do this. I want to see if the input key is greater than 0. Because if it is greater than 0, we do this, and if it's not, we spin it around 180 degrees. Sick. And then I plug U in. I may have done that logic backwards. Shouldn't have said that. I nailed it. All right. So you can see here that we've got. Why do these materials suddenly break? All right. Anyway. So what that's doing is that's kind of like creating that thing for me, and that those pieces are in play. Let's go ahead and do the other ones and kind of work through similar logic, whereby if I'm getting the next one, which is going to be either a 2 or a 3, 2 meaning 3 and 3 meaning 4, because sorry, I'm going to say if you're greater than 2, that means it's a cross 4-way intersection, and if it's here, it's a T intersection, right? So let's just do the same thing again and say to it, hey, if you are 4-way intersection, if you are that, and then I put you in here. Now this won't be right either. And that's because it's putting 1 at each location, each entry point, exit point. That's fine. All we have to do is get that, and because they're all clustered, I can grab this and I can say, hey, I want to cluster all of those points together. And that should give me something. It'll actually take the rotation of the first point if I haven't told it to reduce that attribute, which is probably fine for most cross intersections, as long as you're not doing some weird angle that I might need extra safety checks to turn it into a roundabout or something. Whatever. The next one that I want to do is how do we deal with the T intersection? Because the T intersection actually has to have some sort of directionality to it. We need to make it point towards something, right? And that's actually not as bad as it sounds, because I've got 3 points coming in, right? And if I've got 3 points coming in, what I can do is I can get the distance to the raw intersection. And we know the raw intersection should represent the center of the intersection, right? Which means, click the wrong button. Which means if I get the distance, but I output it as a vector, That's now going to tell me how far along the x, y, and z axes that other point is, right? If I get that to the center of the thing, what I'm able to do is normalize that vector, and that will now give me a direction vector that points at the thing. You know what I mean? You represent my intersection here. So what that means is if I've got one pointing this way, and one pointing this way, and one pointing this way, these two cancel each other out, right? So in theory, adding all of those things together should give me the final direction, because the two are pointing away from each other. Tease, what a concept. So like, because of that, I can kind of say, hey, I actually want to normalize you, collapse and merge, not just your position, but also the distance attribute we just threw together. And then after that, I want to get that direction vector, and I'm going to make a rotator from x. Oh, and I probably want to set you to be the rotation. Yeah, cool. Yeah, great. Sweet. I think that'll work. Cool. I need a T intersection. Did I mess up some logic here? That is, oh. You were too quick on that. You already knew. This is a setup. All right, so that's actually now pointing down there. And because of the angle that I had, it's a little bit off. You know, if I had more than an hour to build an entire procedural road system and building system, I would have some slightly nicer controls in here to balance it. And honestly, even just dropping in actors in the world for like course correcting and stuff like that makes sense. But we don't have time. So what I've got now is I've got all my intersections and stubs now kind of appearing. And you know, realistically, yeah, I could spawn my spline meshes, and we would have something that looked like this, but that's still not quite right. So what I'm actually going to do is, remember I mentioned I had those, you see all those bright red arrows that we had before? Those red arrows are tags. So I've actually given them a tag inside the level instance with the word connector on them, which means that when I copy out the points, I have a nice little thing that says connector. And I can say, if connector is equal to true, go do this. If not, I don't care. You're fine. Right? So if we come back here, notice that all my red arrows have gone. Great. That means that I've now got this information as every single entry point for all of my things. What I'm going to do is from here, I'm going to just quickly make this a named reroute that I'm going to call like broken roads. Split splines would have made more sense, whatever. Broken roads. And this is a little dirty, but it will work. I can attract things. So how this works is there's a node in Unreal called attract. And it says find something within a distance of me and pull it towards my location, or pull it towards my rotation, or pull, you know, you can throw variables through it. And in this case, if I was to get my broken roads and run the attract node, oh, sorry. I want to get this and merge all the points together. For the record, whenever you see something that says they must be n to n or n to 1, that's just basically telling you that you've got a large data set that needs to be merged together because it doesn't know how to deal with multiple data sets. And if I set this attract value to like 1500, and I actually preview it, notice that these points are gone now. Do you see that? What's actually happening instead is this node is attracting these things to it. And I don't just want to attract the position. I also want to attract the rotation of each one as well. OK? And you can now see that, notice these ones, they snapped to face the direction of the connectors. You get what I mean? So I've like not only pulled them there, I've pulled them there to then face the direction. But this, under the hood, is still a connecting spline. And that's really useful, because what I can do is I'll just run a collapse nodes to get rid of anything that's really close within 100 units, which means if this attracted 5 things to the same location, I've now got 1 thing at that location. You know what I mean? But with that said, we're actually now in a good spot where I can go ahead and get this spline mesh that we had. I'm going to disconnect you from there. Woo-hoo-hoo. There we go. Now, this is still not quite right, but it's definitely getting closer. If I was to turn this out and create a spline and plug it in, getting closer, it is connecting to the point. But the problem is that how these work is they need to have their tangents set. So spline meshes by default look at the next point and just calculate what their bend should be. But what we actually want to do is have like a really fixed value that says you come out at exactly this angle and you go into the next one at this angle. Now, fortunately, we have something on a spline sampler that allows us to export the current tangents. So it basically says, here's the numbers that we calculated the first time around. Now, what I'm going to do is over here, just after we kind of collapse the spline, I'm going to say to it, and this is something that is me skipping a step. I'll step you through what I've done, though. I've created a tangent from rotation node. This is not complicated. I literally check, are you the first or last index, which we did. And then I say, if you're the first index, set the leave tangent to be equal to the forward rotation of the node. If you are the last one, set the arrive tangent to be -1 multiplied by the forward rotation of the node. Do you know what I mean? So I'm looking at the rotation, and I'm either pointing it backwards or pointing it forwards. This just is too fiddly, and we're down to 15 minutes. So setting up those tangents manually, I go to here, and I say apply custom tangents. And in theory, that all works. And then we've got ourselves a nice little road system that I can comfortably delete stuff from. Whew, sorry about that. What is going on? Where is my last spline? Wait, no, that was the good one. That's the problematic one. Get out of my life. All right, cool. Sorry, I'm really wary about it. So, I've got that, and I should now be able to say, hey, draw to here, draw to here. That's definitely a straight line, and hit accept, and that will create intersections for me based on these things. We can kind of wiggle that around a fair bit as well. So if I like that, I can then pull this up to here, make you. And I can tinker with this and make this a bit nicer as I see fit. The angle of these is going to matter right now. That's fine. We can fix that. But my point is like getting it to this point is not a huge endeavor. The next part, though, is procedural buildings. And procedural buildings, not as bad as it sounds. What I'm going to do instead with the 12 minutes left is I will drop in the one that I've got, and I'm just going to step through how I kind of set that up. Sorry, if I had about 5 more minutes, I would be fine. So let's all blame the saw guy and pretend that I would have been fine. All right, so I'm just going to step you through what I've got here, because it's actually not that much of a problem. Apparently my splines are, though, but I can fix those values. That's fine. All right, so this seems complicated here, like we're doing big procedural buildings. But I'm just going to hit save all before I do something dumb. So how this system works, it's opened up over here, is actually reasonably straightforward. This is what I'm doing right now to create a building. So this stuff here is literally me saying, sample the landscape, and then the intersection node. Actually, I'm going to turn off this end bit. This is saying sample the landscape and make sure it's near the splines. I'm doing this so that I'm only generating buildings within a radius of the splines. After that, I'm telling it to delete the roads from the thing, which is giving me that result, which has me really suspicious that it's picking up the old spline somehow. We're all seeing that, right? I'm not going nuts. All right, I have a deep suspicion that there's some legacy data from the modeling tool. Yeah, all right. Anyway, so that's now deleting those points from around my spline. Do you get what I mean? So that's all logical. The next thing that I'm doing is I'm giving every single point a value of -1. Okay? So I've just given you a building ID of -1, which means you don't have a value. Sorry, that was more offensive than intended. But I'm then going down to here, and I'm randomly collapsing it onto every 6,000 units or so. And I'm telling those points that their building ID is, there we go, I've done it over here. I've told them that their building ID is their index. So what that means is I'm telling these things, if you're close to one of these, your building ID is now equal to the index of the random points that I created in the world. So if you're close to this point and that's 0.0, your building ID is 0. If you're close to this one over here and it's 0.7, your building ID is 7. And that actually gives me a circular radius of buildings that would be that. Now, because it looked a little weird having kind of spherical buildings, I wrote a little flood fill algorithm. This is really simple. But I'll step you through the logic. This basically is saying, go through, look at all the points that are -1. Sorry, look at all the points that have an ID that we've never checked. Attract all of the -1 points. So basically say, look at you, are any -1 points near you? If they are, they're now equal to your ID. And then I put all of those ones that just got given an ID for the first time into a list that says we should now check what's close to you because maybe we'll find some more. And then if that's the case, it runs itself inside of itself, so it's recursive, right? Until eventually it says if the point count is equal to the number of points that came in, it means we didn't find a single new thing this time around, get lost. At which point we bail out. And that flood fill algorithm just gives me, basically just every one of these buildings reaches out and searches for all the points around it until it hits another building, at which point it's like, no, you do you, and stops. The cool thing is that after that, all I have to do is partition by the building ID, and I can actually see that here. So like if I partition by building ID, that's the shape of that building. Do you see what I mean? Or if I partition by this building, I can see that that one's ended off more squared off. And the great part, this is even more complicated than it needs to be here, but we have a function in Unreal called findConvexHull2D. And this literally finds, I'll preview it for you in the world, this literally finds a shape looking at all the points. It's convex, so I'm getting some overlap, but it's literally just finds the outline of the shape. So if I've kind of like filled up an area and said, you're this building, I can then say, get me the outline of that. If I get the outline of that, it spits this out. If it spits that out, what I can do, and this is a little dodgy, is I deleted the first layer of points from itself, which got rid of these, which meant that I ran the exact same logic on itself, which was find convex hull, and then do it. That then gives me like, I'll preview it here. That then gives me more space between the buildings, because I kind of like deleted the outer lines of every set. Do you know what I mean? So I trimmed them a little bit, but honestly, that worked pretty well. Yeah. Anyway, the last thing you need to know, and this is something that you have a clear reference for when you go home, is I've given them an extrude vector that represents how tall the building is going to go. I randomized the value between like 2,000 and 5,000. And now I know it looks like I've then just been like, draw the rest of the owl and generated this building. But I don't want you to be afraid, because this part's strangely way easier. If you go into your geometry script interop plugin, right? If you open that thing up, you will find this. Whoa, mouse was too high. I was used to shooting around a city instead of like gently moving around it. If I alt drag this box, PCG is doing its best to cover the outsides of this box in walls. And this is how I'm going to show you what I just did in the city, because it'll be a little bit cleaner. First off, if you open this sample, it literally says, find every mesh, create a cross-section of those meshes, which is a function that we have that basically says, draw a spline around them as best as you can if it's mesh data. and then execute PCG building sample. Now, what I did for my building generation is literally a copy and paste of this, and I stuck a roof into it, okay? What I did is not fancy. They've just done it with way uglier meshes. So if I load PCG building sample, I want to step through this logic with you in my last 5-6 minutes. What happens is it goes through, and it initially adds an attribute called grammar. And I understand it's quite funny to have me up here getting an American audience and being like, let me tell you about spelling and grammar. All right, only a few people thought jokes with the Commonwealth were funny. Thank you. But what we're going to do here is we get that, and there's a value here. So this is adding grammar that has the value main floor, and then it says intermediate asterisk. And what that means is add one main floor, and then add as many intermediates as you can fit, okay? And if I go to this duplicate cross sections, it says a main floor is 300 units in length. An intermediate is 250. So it goes ahead and it adds the main floor, and then it tries to fit as many of those intermediaries as it can. And I can add as many of those extra layers as I want to get those different things. Now, this next bit looks complicated, but ultimately what it does is spline to segment. Spline to segment gets the spline and breaks each section off into an individual segment and lets me look at how big that piece is. So I can actually find out how long each wall around the building is. Do you get what I mean? And if I know how long each wall around the building is, select grammar says if it's the main floor and the size of this piece is greater than 499 units, add a C and then a W or a W1 as many times as you can, and then a C. So that's going to add a column, wall, wall, different wall variations, column. If I go to here, I can see if it's less than that, because it's the remainder just says select, it says add a column, as many walls as you can fit, and then add a column. Do you get what I mean? And like this logic is super powerful because you can actually use it. There's a great document that we have called Using Shape Grammar with PCG that breaks down the different kinds of brackets and what those mean in the context of setting up language to define these things. But if I go back to my sample from just a moment ago, this concrete wall is because I never set up a version of it to handle a size between here and here. I was like, look, it's a demo, just make it concrete. And then of course it's like the only thing that I see when I look around. But the rest of the time, I can see doors, I can see walls, I can see whatever I need. And if I actually look at the building generator that I made, I'm literally just, I get the extrude vector and I spawn a dynamic mesh. That's all it takes to generate the roof cap for every single building. This is exactly the same as the logic that I was just discussing with you. This is a straight copy paste, right? And all I've done is I've set up the grammar rules to have, this has main floor, intermediate, and upper. And upper is the reason that I've said maybe try and fit an upper if the ratios are wrong, which is I probably shouldn't have let it do more than 3 uppers because more than 2 uppers because it looks weird. But you can see now that when the 250 is within a strange range, it's like, all right, I'll add some art and try and fill that out to the size. Do you get what I mean? And like having that in there just is all it really took. And I could be feeding in that information with extra things. Like I could grab the grammar rule based on are you on the street or are you on a lane? You know, so if we're on a lane, I can then be like, don't add doors, that's weird, add fire escapes. But if you're on the street, then we care about doorways and things like that. So I could use additional things to populate the grammar rule sets of what is and isn't acceptable at those locations. And grammar is really useful, but it's definitely been named by, like it's an engineering concept, in my opinion, in this context. And what that means is like a lot of people don't look at who looks at art and says, I need grammar? Like, you know what I mean? So like, it's really easy to kind of miss that information. And again, like I want to flag that this was a very, very simple road system that I kind of threw together here. And that also, honestly, to be blunt, I think a lot of what I've done here is going to be like single nodes down, like in the future for PCG. I've just done this quite quickly. But I really wanted you all to see the advantages of like splitting up data, dropping it into different kind of like data sets, and basically being like, how do I kind of keep the logic of the spline and gradually, you know, give that information? How do I keep the logic of the intersections and give that information, pass them between each other a little bit, et cetera, et cetera. So I hope we're down to the wire on time on this one. I hope this has been useful and wasn't too much of just a random nerd rant, but thank you all very much for your time.
Hello. All right, let's get started. Hello. All right, we are here to talk about UI in UEFN, and we're going to go over some new techniques as well. All right, it's an awesome turnout. Thank you so much for coming here. My name is Derek Diaz. I am a UX UI director on the Fortnite ecosystem team. And well, I love building game UI, and I also love creating tools for creators, for you guys, to help empower you to make awesome stuff. All right, let's move on to the agenda. Lots of stuff. So we're going to cover a whole lot of stuff. We're going to talk about how we can use devices to get data to drive UI. We're going to go over how you hook it up, how you can use UI materials to spruce it up. We're going to pull it together into examples, HUD, playground, and talk about verse. So got a lot of slides. So hope you're ready for that. Let's go ahead and do that. Just kidding. We're going to do it all in gameplay. Who's with me? Let's go. No more slides. All right. So we are going to head over to the Flush factory outlet to talk about creative devices, and starting with the HUD controller. So the HUD controller is a creative device. It lets you configure your HUD in lots of different ways. So here's the standard Fortnite HUD. You have your minimap top right, your vitality in the bottom left, your quick bar on the bottom right. Let me grab some items. So you can control all those things. Oops, move things around. That's never happened before. Hey, we're back. So the HUD controller device lets you move things around the HUD, but it also lets you totally reconfigure certain parts. So here is what we call the player information. So what we're looking at here is a custom widget. Let me switch over to, this is UMG, our UI editor. So this is a widget that I made. It's a bunch of stacks of text. So this is a view model that we added through the view model button here. And this provides all the data from the controller device that you can hook it up to drive your UI. Switching back here, so I can walk over here and cook myself on this flaming toilet. And notice the health value and the health data goes down, right? You pick some health up and get some shields too. So all that data is there, and we can look at it a little bit. So it's structured in a certain way, and all these data view models follow a certain pattern. So we got player information at the top. In the middle, there's state data. Are you disconnected? Are you being revived? Or you can use that to control your UI. And in the bottom, there's a bunch of different data about your health and shields in different formats to create the UI that you need. Another piece of UI is the selected item. So this is also a custom widget, and notice it shows you what's in your hand. You can see the values change on the ammo count. Now, it follows a very familiar pattern. We have state information about that item. You have count information, largely about ammo and so forth, and you have your name and imagery of your ammo and weapon. Now, a new thing I'm super excited to share, let me scoot it over here, is a view model for a quick bar. So this lets you, there we go. On the left here is basically the world's worst quick bar. It is showing you all the debug data. See that it is focus changing? So this is the raw data view. Follow the same pattern. This is set up for imminent release in 36.0. Now it has state information, the count information for items, very much like the selected item. Also has durability information, so you can figure that the way you want. All right, so the next thing we're going to do, this is a bit of a speed run, we're going to head on over to so what, past these creepy guys, okay? And we're going to talk about how we hook it up. All right, so let's make something not so terrible, barely maybe. So here's a custom UI. We have our health 80, our shields at 20, our player portraits in the middle, your item that's currently selected at the bottom, right? And if you look on the right, we have a quick bar, something very different from what you normally see in Fortnite. We have the text showing for what's selected. Okay. Some animations now. All right, so let's pick up this and go stand on our flaming toilet. So notice the animations coming out from your shields, the delta value of how much damage or shield damage you're taking floats up top, and same thing with health. I don't want to get eliminated here, so let me back off. Similarly, I gotta spend some, I'm a terrible aim. If I spend my magazine, there you go, and now I change to an empty magazine item, you see the animation in the bottom, it turns red, it says like, right? So that's an animation. All right, so let's look at how this is set up. All right, back to UMG here. All right, so here's our widget. Now, so this is the player information view model that I showed you before. It's hooked up, or we're going to hook it up a little bit. Let's start by hooking up the player name. So we're going to click on the view data binding section, click on the name, that text element, text block, and we're going to choose a text property. And now we're going to use this browser to pick from the view model, that data structure, we're going to pick player name. You can also drag it from here, right? And so now this is passing the player name to that text block, right? And we can do the same thing for health here. Our health value is displayed as text. We're going to add it here. We're going to choose a text property. Now, the one difference here is that that text, that health value is actually coming in as a decimal value. It's a floating point number. So we're going to choose convert it from a float to text, right? And now we're going to choose the health value in that same way from the view model. So that's how you would set up passing a number to a text field, to a text property. The last thing I want to show on this one is how you would set up the player's portrait, the avatar portrait. So we click on the add widget for that image, and then we're going to go ahead and pick the brush. And now we are going to do another conversion function, not float to text, but we're going to choose make brush from soft texture. What's a soft texture? So it's like a lazy loaded image, so it's not all preloaded. So that's the way the data structure works, or player information. It comes in as a soft texture. So we're going to choose that player avatar icon here, and now that's going to be hooked up. All right, now animations. So we saw some pretty cool animations, or some okay animations. I did them with myself, so I'm not a UI artist. So we have the heart popping up with the when you're losing health. We have shields numbers popping up and the shake. And when low shields happens, that kind of highlights. So here's our three animations, the animation sequencer. And you can kind of scrub this and see how that works, right? So we made those animations. How do we trigger them? All right, so triggering animations can be done this way. We have 3 when statements. We add a condition. I added them here in advance. And we set this up to say when the health data from that view model, the health delta, which is to say if you take damage, it's a negative number, is less than 0, we're going to play an animation. And of course, we're going to play the lose health animation. Same thing for shield delta. And for shield, when the low shield hits, we're saying, hey, when your shield is less than 30, play that low shield animation. All right, there's a little bit of a speed run. Let me jump back here. OK, so let's go ahead and turn that off. And we're going to head over to past the creepy guys, yowzers, and we're going to go talk about UI materials over here at the Pizza Pit. All right, so UI materials. So UI materials are a way to enhance your UI. They are highly customizable, 2D art, and they can be controlled from verse code. They can be controlled from UMG. And so let's go ahead and pick up some floating pizza here to have a look, because why not? Magic pizza. All right, so here is an example of a meter. Meters are really common in UI, right? Now, all these are from the same material, right, with different properties. Here you see rounded edges, you see the sharp edges, the gradients. They all look really different, right? Here's some more. Cool 3D effect on the bottom here, right? Now, all these materials are from the same material set, and you can actually go grab them from the UEFN UI feature example that is in UEFN. So they're sitting under a folder called UI library there, I believe. And so we can have a look at these a little bit now. Okay, so you'll find this set of materials there. And these are a bunch of different meters and bars. We're going to look at these in a second. And things to help you make textures more interesting. You can right-click on a material, a UI material, and you can say create instance. And I have a bunch here. But let's go ahead and make let's customize a very neutral one. So this is our linear meter, good old linear meter, right? And you can change a property right here. And you can see it's a meter. It's doing what meters do. You can also set rounded edges. It's a little bit aliased, right? So we can address that. We can change slant, right? Make it kind of interesting that way. Even do some crazy 3D effects, because why not? Notice this, this is handy for a lot of times. You want to add an end cap color, so it looks easier to see. And you can make that rounded as well. All right, cool. Whoops, there we go. And lots of color options along a gradient. You can colorize the bar meter and the background colors very separately. It's hard to talk while doing this at the same time. All right, so here's something I threw together literally in front of you in 2 seconds, and it looks very different from what it started with. No? Cool. All right. So we have many materials there, and we're going to go through some of these here now. All right. So this is a segmented meter, and it has rectangles at the top, circles. It can be configured to have triangles. It can also be configured to use a texture of your own, or just some from the library that we've included. They can be configured to be discrete, so they're not just continuous and smooth. This could fit your gameplay better. And this is another one where we have that stroke, right, and inner fill colors. Now, you might be asking, it's a texture. How do you do that? You can't just do that, right? So we're using signed distance field images. Signed distance field images, it's a format for making a raster image optimized to let you, say, have sharp outlines at different sizes. So this fish is just plain old texture. When you blow it up, it's pixelated. This is an SDF version of that, and as you see, it's smooth edges. This lets you do cool things like outlines and borders and other things. We use this quite a bit here. All right, moving on, next piece of pizza. Radials, really handy, making UI for lots of reasons. This is all from one material, pretty handy. You can see they can be continuous or smooth. This one in the middle has some pretty cool gradient things happening. All right, I got to keep it moving here, so let's go on to the next. All right, so this is a texture meter. Now these are SDFs because you can see different treatment happening. This bottom one has a border around it. There is an inner animated texture happening on the fill here. And and these are just really cool. You can actually, we provide a bunch of these. We provide a bunch of these in the library. This is just a snippet of them. So here's a bunch of those backgrounds, and you can just go ahead and change that to any number of those that we have. All right, pretty easy to use. Here's some other ones. The green one has a property to blink red when it's low. Great for showing low health or low values. And this is another, maybe it's a health and mana indicator. All right, cool. Let's go on. Here we have SDF icons. You can see they scale really well at different sizes. All right, now this is showing off the different shadow capabilities. You got a top-down shadow, offset shadow. These shadows are different angles than the main image and different colors. Over here we have inner or outer outline, inner outline, and shadow combinations. Lets you do a lot of cool permutations. And this is demonstrating that you can apply an additive blend mode to a material as well. So let me maybe close some of these things. So if we were to, you can see it right here really well actually on the ice cream cones, how it comes through. So that's just right here, additive as a setting. All right, jumping back into it. So a lot of texture effects that we can do with a material called texture effects. You have tiling with animations. You can do a bounce. That heart has 3 different bounce patterns on it. And the bottom character has a warping effect. Maybe when you're dizzy or something, you can use that. There is a pixelation and another bounce. I like the one on the right. It can be used to create like a jukebox or a slot machine type animation with multiple icons. And this is pretty fun. There's a lot of different coloration capabilities with animations as well. All right, and picking up this last piece of pizza here. This is our mask texture. So what happens here is you can tell the material to allow the inner image to poke through in different places, in different ways. And you can configure it lots of different ways, and you can control it also through animation sequencer. Okay, and let me jump over here to show that. There we go. Okay, so this has a nice feature to preview the mask. So you can see how I can move this. And this is how you can configure what part will poke out, will come through. And you can change the shape and a bunch of different properties. Okay. Let me walk over to this pizza and pick this up. All right, so now we're going to apply a bunch of those different materials to another version of the world's worst HUD. So all of these images, all of these materials are being data-driven by the player vitality information. So let me show that data binding briefly here. I'm going to jump into this. So all of these, or mostly, have the same data binding. So bar, that's this one right here. All we're doing here is we're grabbing the brush of that image, and we're using a parameter conversion function called setScalarParameter. And what that's doing is letting us drive that health normalized data, that's your health between 0 and 1, to a parameter that we type in called progress. And when we look at that, as you saw previously, these materials had a property called progress that when you change that value, it moves. And they're all the same, except for maybe this one here. This one, we're changing the bounce speed parameter just for fun, just because. All right, so let's walk into here, and we see our trusty flaming toilet, and we can watch those values change. On the bottom right, the character bounces more slowly as they take more damage. Bottom left, they kind of scoot from green to red as they take more damage, just because. All right, let me turn that off. And we are going to head into a room right here where we can look at applying those materials not just to your HUD, but also to other devices that provide data. All right, so let's look at a timer here first. OK, so on the top right here, what you can see is the view model data for the timer device. It has the values of time, the display text, which is convenient to pass to text fields, and the states. Is that timer paused? Is it started? Is it an urgency mode where the behavior changes? And if we were to, so let me walk over here, and you can see this is a default UI for that timer, right? Not terribly interesting. It's a default. And on the right here is going to be a custom widget timer that I made. Actually, you can see this on the expo floor if you look at the LLM demo where you shoot targets. So these are all using those same materials. And you can see on the top left, that's the data view from the view model that we're just using to pipe into the materials and the properties on the right, on the widget on the right. OK. So the next thing we're going to go look at here is a skilled interaction device. So let me just demonstrate this thing first. Skilled interaction device is a device which creates a minigame, basically. It can create 3 different types of minigames. Here it's making a stop the bar when you're in the middle color zone. There we go. It can also be used to do a radial version of that. Same game, and it has another built-in format for radial. All right. So this has a fairly complicated view model, actually, but it does allow you to create your own widget and utilize all that data to make your own interactive experience. So we have your labels at the top with the header and description, the meter values for the current meter, the good zone, the perfect zone. You saw 2 colored zones there. The success failure count and more colors on the bottom and so forth, right? So let me show an example that uses that to create a custom widget. Now this one's actually not using a lot of materials. This is more texture-based, but it's a nice bright example. So you can see that the current value is changing, and it's animating on the right. So now, I actually probably set this up wrong at the last second, and it shouldn't give me a success just then. But you get the idea. You see that success and failure is changing. Oh, OK. So, and this next one I want to talk about is called Stat Device. This is a really versatile device. It's great to use for just anything that has sort of 2 levels, like a level, a value, and once the value hits some threshold, the next level can level up. So XP and levels, for example. This has name and color and your state information, is it at maximum, and all those values I just spoke about. So this is really hard to see. It says luck in the bottom left corner. That's the default widget of this device. I just called it luck and gave that icon. So that's a tracker on the screen, what you get out of the box. So we're going to look at a custom version of that now. We're going to run over here. All right, we're going to pick this up. Holding pizza still. All right, so top left corner is that data that we were just looking at, the sort of debug view, if you will. I chose that color pink and the alien head, and you see added those to the pickups there. In the middle, that radial is a widget counter that's set up with the animations and the data bindings using the same principles that we went over before, using those same materials that we just looked at. I'll just kind of walk through here, and you can see how it's triggering animation. And once it levels up, it's triggering another animation right there. So you can use this really for anything you want. It doesn't have to just be sort of statistics-based or stat-based. All right. All right, now we're going to go look at bananas, collecting bananas. This is also using the stat device. You might have seen this also on the stage demo yesterday. So here we can grab the first one to start it. And here we can pick up bananas, and they get added, triggering animations. You can also reduce it. I just want to demonstrate that you can reduce it. And you can play animation when it's done. So that sparkle was a really cool SDF texture where we're changing the different settings such as glow and feathering property. All right, let me jump over, and I just want to show that material. So this is using the segmented meter. Here we go. Let me make it display a little more clearly. And just as we change that progress value, this changes. And this is just an SDF texture. All right. Oh. OK, so for the next part, we are going to head on into what I was calling the HUD playground part. All right. So let me turn that off and grab a couple weapons. OK, so HUD playground. So now we're going to look at how we can apply all those principles to pull it together to create sort of full-on HUD conversion, all using a controller device. Let's start with number 10, because it looks like this. Awesome. So this is the data that you have to work with. And here's the world's worst AI. He really never hits me, but maybe this time. There we go. I don't hit him either. If I pick this up, I get another item. So bottom right, or the bottom part of the screen that's the quick bar custom widget. This is that debug view that I created. So not very compelling UI, but this one looks more interesting, I think. All right, so here's kind of a sci-fi looking UI. Wow, I am low on health. Maybe I'll grab some health. OK. So you see I changed weapons, and we see the quick bar changing, and the selected item changing. Now, looking on the wall here, so if you were to go to a controller device, this is demonstrating how you would configure the quick bar, the custom UI for the quick bar. This is a new feature. Here we just chose quick bar slot style 1, and you see it's set up to be, let's go down the list, right? So the quick bar key binding layout is on the bottom. The orientation of the bar is horizontal. We're saying we will modify the custom quick bar layout. And we're telling it to be aligned to the bottom of the screen, bottom center, with the anchor bottom center. And we're giving it, we're scooting it up by 100 pixels. And that's how it gets in the middle there. And actually, we can look at the quick bar briefly here. So what you do is you create a widget for the quick bar slot, a custom widget. So let me zoom into this guy a little bit. This is a placeholder image. It's actually getting data from the view model. So that's why it doesn't look pixelated when you see it. So here's the view model for the quick bar. It's called item entry view model. And all the bindings are configured the same way that we went through them before. And I'm not showing the weapon, the ammo quantity and the magazine size here. I turned that off here. I don't want to see that here. For this next one, we'll have it on. All right, this is a similar one. Let me stand on this campfire, and you can see the health values change. So here we're showing your shields with a percentage number and kind of a cool format for health and shields on the left. And a different take on a similar UI theme. All right, we're going to go through some of these because they're all pretty different. I love them all. I love the colors on this one. So here we have the rarity color comes into the quickbar view model, and we're using that to set the background color of those. So that's why this one has a different color. So all these are using the same materials we went over before. All right, here's one with very thick borders. All right, this one's interesting, very artistic here, and look at the animation effect that can be triggered when you use the quickbar view model with a custom widget. All the little detail textures are coming through as an SDF with shadows and borders attached to it. This one is a bit of a kit bash, different take on that. This is kind of, I think, slightly better or more interesting. I love how the health and shields look, so let me grab some shields. So that's the SDF meter material for the shields and health bar, and they're just overlapping each other to create that effect, but they're independent materials. All right, here's a totally different take on it. This is sort of a CRT scanline effect. Big chunky graphics, I love it. All right, this is one of my favorites. I guess I keep saying that, I think, probably. But this is a fun one. So here we are modifying one of the materials. I'll show you in a second. But so here your health comes across, or your shields is represented by the radial meters. And once you lose shields, you'll see the image in the middle will start to turn red from the outside in. So you create this really cool effect. And we're running animation to trigger the background color changing as well. I forget at what point I made it you die, so let me be one more, push my luck. Okay, so, and cool circles for the quick bar to match that style. Right, let's see here, and I think number 9 here is, all right, so here is a wood grain, because why not? Because we can. Maybe not fitting the environmental theme I have here, but here your shields and health are radial meters, and your weapons are also encased in wood. Right. Okay. Another thing you can do is you can use those materials to show the amount of damage you take on the health bar. So that is more. So that is brought to the attention of the player. It highlights the damage you take, like this. See that red? Common in fighting games and so forth. But it's a good usability pattern. And it works both ways. So let's look at that real quick, because that's a special case. All right, so here is that widget, or a version of it. Let's give it a second to load here. OK, cool. So now this is using the Delta material. We didn't go over that in the material showroom, but it's in the UI template. And so you see it's configured to, we're setting the progress value of the material to, via set scalar parameter like we demonstrated, to the health, just like you should. And then we're also setting a parameter called delta on that material in the same way to the health delta value. So that is how you configure the value of the delta. And then we play an animation over here that triggers that. Or rather, play an animation that makes it do that transition. And then we trigger that animation through the same system I described earlier. So we do a when condition, and we say when the health delta, really health delta, this could almost be just as not equal to 0, changes, we're going to play an animation. And we're going to play that animation I just showed you, of course. So that's a way to show the health delta value. Oops, let me jump back. All right, other cool things. Teams, you see that I have those test players on the left there. So I like this one. Here we can show all your team members in very different ways. All right, cool. How's this done? All right, this one's a little bit more complicated, but it's really not that bad. Whoops. Let's go to, first let's look at the widget. So this widget is built the exact same way that all these were built. We have text, and player image, and a bar meter being set up to the player's health, right? But now there's another widget that we're using called, I just called it the root. So this is called brawler widget, and this is another widget. Now what this is doing is this simply has a stack box in it. A stack box is just a layout component. It allows you to put multiple widgets in an order, vertical or horizontal. So this is our player information view model for health, vitality, and so forth. Now there's an array in here also, right? So so this uses the array. So this stack panel is configured to use the view model extension. There's a button you click, add view model extension. I had already clicked it, so you're not seeing it. And we're choosing that brawler widget that you saw before, right? And we're choosing the view model that it has for player information. That's the vitality one. And you can just set the preview of how many you want to show here, so you can get an idea of how it will look. And you can set the template, the spacing and alignment and so forth. And then there's a special binding you do for that. Here you're going to go to the root of your widget, and you're going to choose the stack panel extension, and you're going to choose set items, and you're going to then go back to your view model, and you can choose this one right here. And that's going to populate this stack box with everyone in that array, which will be your entire team. OK, so that's how that's set up. Variations. Cool. I love this one. I do like how the green and blue have that animation effect. This is using the SDF texture meter set to vertical. And you see your teammates are blinking red because they're low in health. Another version of this is you can set it up with conditions to alternate like this. I think it has a nice look. Honestly, if you saw my bio slide, it said I've been working on Fortnite for over 10 years. So I am so delighted to see very different UI within Fortnite. And here is also one of my favorites. This is just a sort of pop art style. And I probably have full health, but full shield, so I'm not showing shields. You don't have to use all the data in the view model. In this case, I'm ignoring the shields information. Come on. Oh my gosh. There we go, shield broke. Now health will go down. OK, cool. So that's a bunch of examples. The next thing I wanted to do was talk about a new feature, a new technique for making UI called material block. This is something you do in verse script. All right, so let me go through this portal now on purpose. And we're going to head over to the arcade. Here's those test players that were showing up on the HUD. OK, so here we are in the arcade. We're going to talk about material block. Let me step on this trigger. All right, so what we're looking at here is on the top of the screen, we see the radial meter, the stripes that are animating, and that big blue square, light baby blue square. I configured it to change when I move forward and backwards, just to demonstrate this. When I move forward, the value increases. A value increases, that's changing. all those three materials differently. So the meter, the radial meter, of course, goes up and down. And the stripe meter changes its speed, and it will eventually even go backwards. And then the one on the right is using a dissolve effect. A dissolve effect would be really cool for things like introducing a menu, a pop-up menu or something, or any type of messaging on the HUD. You could animate that through an asynchronous loop inverse. All right, so, and the character in the middle of the screen, that's just there to demonstrate that's a texture block. We'll look at the verse code in a moment here. And then below that is just a text block, so these three are some of the main components now within the Verse UI API for building UI through verse code. All right, so let me jump back over here. And all right, cool. Here we go. Here's those three material instances. And just to demonstrate, when I change this dissolve parameter, you can see how this behaves. And it has translucency or transparency in the background. So this is a really simple one. That's all it does. This is a custom material. You don't need to use only what's in the material library provided. You can just make your own. And this is a meter we've seen plenty of so far. And again, we're just changing that progress value, and it changes. Now, you'll see all the properties here are all going to be accessible from verse code. So you can do any of these things through verse code. There is a range min and max. And thickness. And then the stripe material simply just has a speed value, just for demonstration purposes. OK, so we're going to jump back here, and we're going to look at the verse code. Here we go. Let me open up this is just a verse device. Here we go. All right, here's our code editor. Let me bring it over to this screen. OK, cool. So this is a really simple file. Up here, we just have some triggers that I added that you saw in the room there to step on. That's just kicking off the UI. What I want to call your attention to first here is this section of code. So what we're doing here is we're making 3 materials, right? One for each of those meter, or those images that you saw on the screen. So here's a radial meter. We're just calling it radial meter. And we are making an instance of the editor asset that I just showed you, which is that radial. We are just defaulting the progress value to 1, just because here. And you can add as many properties as you want here to set defaults. That's the same thing for the stripe material. We're setting speed to 0.5 by default, and for that dissolve material. So we call these radial material, stripe material, dissolve material. OK, and this is just the verse code that's setting up the event triggers on the floor so I can step on things and the UI changes. This is the definition for the text block that says this is a text block over here. And so this is now the next interesting part. So here are our 3 material blocks that we're creating. So up here we made the materials, and we set up some default parameters. And now here we're making a material block called radial material block. and then we are setting its default image property to that radial, to that material over here. And then you also want to set the default size. I just chose 400 by 400 over here. And then we're doing the same pattern for the stripe material block and for the stripe material and the dissolved material. Really simple, clean example. I wasn't going to get into too much on the verse code side for displaying UI because there's nothing special going on here. Actually, this is actually not even a great example of displaying verse code UI. But let me just kind of talk it through for a moment. When you look at, where'd the gameplay go? So here we have those materials in a horizontal row, 1, 2, 3, and then you have the texture below it with the player portrait or the portrait, and then you have that this is text block below that. So there's 3 rows, and then the images are in 3 columns. So that's what this stack box structure is doing. We're making a vertical stack box here, and we have 3 slots in there. 1, 2, 3. So this first slot contains another stack box. That's horizontal. That shows our material blocks. And then the next row is our texture block. So all we're doing here is we're setting that widget to be the material block in the UI. And then we are showing that UI over here by calling add widget. When I step on that trigger, we're calling on show, and that just shows the UI over here. We're also setting the radial material progress to 1 here, just because. But that's the next thing I want to talk about over here. So if you look at the bottom of the screen, I think this is really cool. Now, why is this cool? Because this is a very new feature, just released, and you couldn't use materials before in Verse. So you would have to do texture shenanigans in order to create a meter, some of those basic UI elements, right? So now if you want to just create a meter and show leveling up and so forth, all you do is you just set the property directly from Verse on your material. So here, when you step forward, we are increasing the value of those materials parameters. We're saying progress equals progress plus 1. We increment speed by a decimal by 0.1, and we change the dissolve value by 0.25, just for a demo here. And we do the same thing in reverse when you decrease the value. Okay, oh gosh, 2 minutes left. Oh my gosh, I went too long here because the cool part's next. Okay, the cool part's next. Let's take everything we did and apply it to a example. All right, let's go push that button. By the way, my button was made first, just saying. Okay, so we push the button, and oh, we got some wolves and a boss. Okay, so you have your quick bar slots on the right and your player information on the left, your vitality. That's all the same from before. But the wolf values, all that UI in the top left of the screen, that is all completely material block, setting material values from verse code. The text is changing when you shoot them. And okay, like this guy, actually, I set him way too strong, so I'm gonna stand back here so I don't get eliminated and run out of time. So yeah, cheap shots, I know. But now, notice when I eliminated the wolves, I was in the top right of the screen. I am level 2. I have 2 skill points, and that meter moved, right? And when I eliminated him, I get just tons of XP for that. So we'll see that jump a lot. So that meter rolled over many times over, and now I have 10 skill points. I'm level 6. Okay, that data's not really being used right now, right? But it very easily could be used, and that's all done just by setting the value on that meter. And those images, those textures that we're seeing are SDFs, and we have a UI. So we push the I button here. All this UI completely made in material block except for the text, which is just text block. So this is the same meter as that meter, right? Just scaled up different properties. And I can spend some points. I have 6 points to spend, just enough. This meter is filling up as a material block, segmented meter. And when I fill it up all the way, this guy glows over here. We're just setting parameters on that, telling it to glow, turn yellow. That's not a new texture. These are SDFs. And this says max level. And OK, I want to spawn these guys a couple more times. I know, it's no fair. But I can't even hit him when he's not even moving. All right, so we don't need to fill it up completely, but I can go ahead and, here we go, another one. Cool, OK. For the last thing I have is just a thank you screen. I know I'm out of time. So thank you for the team that worked on this. And thank you all for attending.
Hello, everybody. Here we are talking about the things that we love best, which is to say making great game experiences. My name's on the slide, so is my colleague from Epic Games. Won't say it to you, but you can see we're in batch mode. We're all about efficiency, so you get two of us at once. Don't be confused by the naming. Now, what can we say about games? We know that they are visceral, graphical experiences. Quality matters, performance matters, and this space is incredible. I'm always impressed by generation on generation, not just how much the hardware improves, but the way in which the humans utilize it, leverage it to create experiences that have not been seen before or otherwise amaze and delight our users. And so you can dive into the tech. We can talk about the way in which the high quality that's being rendered onto screens, and in the mobile space where I spend a lot of my time, the screen resolutions are incredible. You know, they go way beyond what many of you might have in your flat panel TVs at home. But it comes with constraints, and you have to be inventive around those. I think it's fair to say that everyone that we're speaking to today has a mobile phone, has a smartphone, and you use it for so many things during the course of your day. You want to carry it with you for your email, for your socials, and maybe for a bit of gaming. And so we have to play fair, we have to use the resources wisely so that you find that you're getting the best out of your smartphones. And that's a challenge for many a mobile game developer, and something that I feel that people at ARM, where I work, have something to offer back to help you get the results that you're looking for. So, everything comes with a cost. We know this, whether you're on a PC, whether you're on a mobile handset, whether you're working on a console-based experience. You have to invest the GPU time, you're spending the power, and you have to make sure that you're presenting at the right quality bar. Everything matters because speak all you like about the tech, it's about the user experience that you render, the expressions that people come away with after they play your game. So how do we work with this? How do we work with our finite resources in order to deliver the results that we're hoping for, that we want to offer back? There are many techniques, some of which are well established in game development law, others which are more novel. So understand exactly how to arrange your data, minimize the amount of traffic, utilize your CPU and GPU as best you can in the work that they do. Super resolution has a great history to it. And when it comes down to it, it's a cheat, like so many of the things that we do in graphics. We start with a low resolution image, complete that, and then via some magic that we might think about, we blow it up to the resolution of the screen, and how we wish to present this as a final result. The techniques themselves have come in many flavors over the year, and we can classify them into 3 buckets now. We can talk about spatial resolution, which is essentially a history-free experience. Here are some pixels, make them bigger somehow. Spatial temporal, which brings in history. How are these things moving in my scene, and where are they situated? Now make it bigger. And amazingly, as we've seen in high-end experiences on PC, on console, ML is finding its way in, as it has in so many problem spaces. Work in a way that intuitively we can infer what these graphics should look like. Now, we won't be talking about ML here in this presentation, but stay tuned, watch the space. One day we will. We'll concentrate on spatial temporal. And we need to make sure that when we're offering these solutions, they appear at quality, but also appear within the budgets that we're talking about. So can you render in time? Are you sapping your battery dry? What's the overall performance characteristics? And this is where we talk a little bit about the history of the technique that we're offering, accuracy super resolution, or ARM-ASR. And we're building upon work that was offered open source by our colleagues at AMD in Fidelity FX. So FSR2 is a spatial temporal upscaler, and we've seen it in quite a few games that have shipped over these last few years. It's robust, it offers a high quality set of results. And beyond that, because the game development community regards it as a mature technology, we thought this was going to be a great place to start. If you already know the APIs, we're asking you to go on a familiar journey on some different hardware. And that makes sense. But what about FSR2 in and of itself? The graphs that you'll see on these slides speak volumes. When you're rendering for games, Many of us will be targeting, say, 60 frames a second. So you've got 16, 17 milliseconds to get everything done. And using, as you'll see on this graph, you've blown your budget immediately. This is taking too long for the mobile phones that we'd be looking at during our work. Similarly, the bandwidth traffic is high. And that's an absolute killer when it comes to latency, when it comes to power consumption especially. Beyond that, you've got the compute task. So many of us love writing compute jobs on GPU. It's fun, it's simple, and when you're targeting the high end, you are blessed with resources. You're more constrained on mobile, and we have to be very, very careful around that. If we're overutilizing registers, if we're having to spill, that's expensive bandwidth traffic, and it's also a performance killer. And so when we look at how we might possibly deliver this into the mobile space, the solution must address each of those issues. And this is where we came in. And when I say we, a very, very broad team around ARM worked on this, including some very talented researchers I'm proud to call colleagues. We liked FSR2. We liked the various features that are built into it. But we needed to make sure that we were both delivering a solution that was performant and left users with the right degree of control for their various goals in the mobile space. So, image quality, great. We already know that using FSR2 as a benchmark or as our guiding light, we'll get there. It's proven. We want to offer high frame rates. That's our goal. We need to optimize. We want smooth presentation. So in other words, we have to be consistent frame to frame and allow for the various sorts of artifacts or features within normal rendering context that may spoil your results. Address the bandwidth concerns. Compute as much as you need and no more. Traffic across your bus as much as you need and no more. And that, of course, leads to less overhead on your GPU, which you may choose to play with in various ways, I should mention. If you have reduced your GPU utilization, you can choose to bank those savings and say, great, we're saving power, we're saving cycles. Or you may choose to fill up that extra GPU time with something else. But beyond all of this, we have to be very, very realistic and understand what developers are trying to do. And as a former mobile game developer myself, I know that device reach is key. It would not really be fitting or helpful, as it could be, if we focus on a narrow range of devices. We can't take a proprietorial attitude. That's not the way to help. So what we wanted to do is make sure that when we offer the solution, it was right there with the developer, trying to follow their needs so they understand that they're going to get all of those users that they really want, the people that they want to appeal to, the users that help them move their business forward, and them to succeed on the thing that they want to do, which is make a game. So, we offer you ARM ASR. We are going to claim proudly that this is a best-in-class solution. We've done the sums, we've done the analysis. We know what we're doing with the GPU utilization, memory bandwidth, power draw. And this isn't just a bold claim, it's a verifiable one. It's available to you and has been since GDC via the Fab Store, via our GitHub. And we want to make sure that you can get your hands on it, try it out, provide us feedback if you care to. We'd love that. But more importantly, if it's a fit for you, use it in your game. That would be fantastic. Whether you're shipping on Android, whether you're shipping on other ARM-based platforms, we love that. And if you find yourself shipping onto other places too, great. Shared success. We're platform agnostic. But we ought to be supportive as well. This isn't just a dash and grab from our point of view. We have this continued mission with our team to keep offering of our best to support game developers. And that includes both the easy integration steps, but also the tutorials to make sure that you can see how we imagine using it and help us move along together when we think about our future roadmap. So let's take a high-level look at the way in which we might render a frame. Highly schematic, but I think it helps in making choices about what fits and what does not. So imagine that you're rendering a scene, and it's got all of its wonderful actors, geometry, terrain, all of that stuff. And this is the first part of the graph on the top. Scene actors in place, frames rendered. Apply some anti-aliasing. and then whichever post-processing that you need for screen-based effects, any UI overlay. Very broad strokes, but this is the typical things you would see in a graphical frame. Good. So what if we wanted to make a change to that and introduce upscaling? Well, we're going to profile that as well. First of all, you can get the best possible case where upscaling is free, which of course it is not. So you can profile at lower resolution, look at what the lower bound is, that is to say the fastest possible rendering time with no adjustments. And then we can look at introducing upscaling into the frame. And then it comes down to a very cold-blooded decision you can make about whether it hits your own goals. In this case, we've expressed this in terms of time. Does it fit within your time budget? Does it net out positive? Something that you might equally well do is take your horizontal axis and say, well, here is my power budget. This is what I'm spending on this, that, the other thing. Does that give me ROI? So, a little bit of evidence. I won't name the phones, but they're popular, they're well known, well used. And we integrated into Unreal Engine, and we tried this with both the mobile renderer and the SM5 renderer, playing with our quality presets to see where we went. And what I'll say is that for the workloads that we looked at, and when I say we, actually I should pause for a moment to acknowledge the work that Enduring Games did employing ARM-ASR, because they actually provided us with this analysis. Much appreciated. They showed us it. We see the figures. We can see how it can fit within a rendering frame's budget. And that helps everybody, I think, understand a little bit about where they can invest techniques like this. As a word of caution, though, remember that we are reducing workload, at least within the fragment portion of the frame. And a tactic that your handsets might adopt is to underclock your GPU as a result. I'm doing less work, therefore I'll run slower. And you may find yourself back at step one. So always profile, always try and understand what's happening within any particular frame. We also put it to the test in other stretching ways. So our content team at ARM produced what I'll call a fairly sophisticated scene with an Unreal Engine in which we enabled Lumen and gave it a very strenuous lighting test. And what we can see is that the difference between using ARM-ASR and turning it off was night and day, no pun intended, in which we can show that it does make this a viable choice to create SM5 loaded scenes with Lumen enabled at a frame rate that makes sense. More analysis, and in many ways, for me, this is a blast from the past, because this scene that was made from Lumberyard's Bistro, open source content, was where we began analyzing the benefits of ARM-ASR. So you can see the full screen, scene rather, that's rendered in large, and then a zoomed in portion. So take a look at that, look for key aspects of the enlarged portion of the scene, and watch for details around the bike, look at the chair struts, look at the clarity of the text. What you can see there, I hope, is fairly convincing evidence that the quality is in place, is available to you if you choose to employ this particular tool. Once again, I'll remind you, don't take my word for it. It's on the Fab Store, it's on GitHub. So with all of that said, I want to take a pause and move us on to the next portion of this talk, which will be conducted by Pete Sauerbrei, where he's going to show you even more of the proof of the pudding. What can you do within high-end titles to achieve even better results, uplift the player experience further? So thank you.
Thank you, Peter. I'm Pete Sauerbrei. I'm the lead of our Tech Mobile group at Fortnite. And here to kind of give you a real-world example of applying ARM-ASR to an actual game. Clearly, the game will be Fortnite. So why would we look at ARM-ASR? Well, in our case, we were tasked last year and sort of the beginning of this year to improve the battery life, the thermal levels, and the performance of Fortnite on mobile devices with the trying to hit a better, smoother frame rate at 60 hertz for the game. And so what we're going to go through today is sort of how we integrated it and what the results are that we're seeing. But let's first start with an actual video showing the actual integration. So what you can see here is on the left is ARM-ASR on, and on the right is it off. You'll notice probably one of the biggest initial benefits is that it will smooth out some of that anti-alias or that aliasing that you see in the distance. There's also a variety of other features that are turned on the left that are not quite as obvious in this scene as we will show later, but this gives you sort of an example of what we're seeing right now with this. And I will point out that this is all running at 60 frames per second, both sides, but with a little bit better look on the one side versus the other. So let's talk about what's going on here with why we're looking at this a bit more closely. So Fortnite back in 2017 or 2018 when we first brought it to mobile was sort of a best-in-class sort of game with running at 30 hertz at the time because it was lower resolution or lower performance devices. But as the devices have gotten more powerful, we've been trying to get it more and more up into 60 hertz. And so these days, as players on mobile are kind of looking for their game, they're looking for smooth gameplay at high frame rates that stays smooth throughout the match, as well as low thermals and allows them to play their game for quite a while. I mean, if it only plays for 15 minutes and your battery's dead, well, that's not very helpful for you. You want to be able to play for a decent portion of your day. So for games like Fortnite, which kind of push the CPU and the GPU on mobile, that's where ASR potentially can come in, and we'll show more of that in here in a little bit. It enables us to reduce that load, and then from that either provide that to the player for longer play times, or provide that as a greater fidelity, visual fidelity. So let's take a look at how we started to integrate it. So this partnership started back after after Unreal Fest Seattle, when ARM talked to us about whether or not we would be interested in some technology that they were working on. And so through the course of that, we took that particular GitHub implementation and added it to Fortnite so that we could actually see how it might work. Took us about a week or two to get it working initially. And initially we started without without the reactive mask turned on. So why is that important? Well, for us initially we were seeing ghosts, sort of a ghosting sort of thing on our playback. So if you see here sort of the inset, sort of the feathers that are on the spear there, they kind of have a sort of a blurred out look. And when this is in motion, you can see that kind of, the motion blur kind of trail behind in a ghosting sort of manner. And so we talked with ARM a bit, and they said, well, let's try turning on the reactive mask. So we did actually that. And here's an example of what the reactive mask would look in this case. The reactive mask itself kind of takes the reactive components, roughness, specular, translucency, and adds that in with the temporal components, velocity and depth data, to generate this sort of mask you're seeing here to help us figure out exactly what should be upscaled and what should be smoothed out and what's missing and that sort of stuff. So with that, we then get an upscale that's much more crisp and much with no ghosting whatsoever, which helped provide a better, more clean look for Fortnite as well. So let's go a little bit more over some of what our code changes were. We did have to make some slight modifications to the engine and to the plugin to make this work for Fortnite. One of those things is that we updated the API for Unreal Engine, the mobile renderer portion, to be able to provide the inputs that the ASR plugin needed. So things like the velocity buffers and the motion blur buffers and those sorts of things, and the color and depth. We also added we also updated our post-process commands to be able to call it properly on the engine side. And then there are some other minor changes that we made, such as using either the mobile scene textures or the deferred scene textures, depending on which one is available, depending on how you've enabled the texturing and the shading in the mobile renderer. These changes made it possible for ASR to work with our optimized version of the mobile pipeline for Fortnite without really adding any significant overhead on the CPU side. The API changes that we have made on the engine side are in Unreal Engine 5.6, so they are available. The portions that we made to utilize that engine in the plugin itself have not made it back yet into the GitHub. We are working on packaging that up and getting it back into there so that everybody can benefit from that. All right, so Peter had mentioned that ASR really helps when you're on the pixel shading side of this stuff. One thing that we see sometimes in Fortnite is that we are vertex bound. So to help us make ASR more beneficial to us, we've been optimizing our content. One of those optimizations that we have here is a landscape optimization. So what I'm showing here is on the left, there is our default landscape that we've been using for Fortnite in the past. High density meshes. Looks brighter on the left because we're using a brighter color for the wireframe, and it's just that dense that it's brightening up the entire image on that side. And you can see that there's actually an LOD further in the distance on that side, which still shows pretty dense polygonal counts for the landscape itself. On the right is our new optimized version of this, where we have coalesced coplanar polygons to reduce the amount of vertices that we're trying to push through the pipe. And that actually helps reduce the overall vertex boundness of our game. We're still vertex bound in a few places, but for the most part, this gets us mostly to fragment bound, which allows greater benefit from ASR. So with that all in place, we've now integrated, we've now optimized a bit more to help ASR, to allow ASR to help us more. What did we see from a performance standpoint? Well, here's our initial graphs. So I'm going to go back to something Peter said, which is profile. Make sure you profile. Because sometimes you'll see something like this, where you're like, QA comes back to you and says, hey, it feels cooler, battery's a little bit better, but when you get GPU times, 30 frames per second is showing a higher GPU time than with ASR than without. And about the same at 60 frames per second. Confused us for a bit, because we could not, there was a difference between what people were feeling with the devices and what we were seeing from performance. So we dug a little deeper with the ARM profiler to get clock speeds. So the GPU clock speeds had dropped with ASR on to sort of bolster what Peter was saying before, which is less load. So the load balancing on the GPUs and on the CPUs reduced the clock speed, which actually made a lot of sense then with our experience from what QA is telling us with a little less heat, a little longer battery life. So don't necessarily take one number and choose to make that your, oh my God, it worked or it didn't work, because that doesn't necessarily always, it's not always the right call here, because we definitely saw this. Now, I forgot to mention that this was an S24 running at 60 frames per second and 30 frames per second with ASR on and no ASR on. Now, to be clear there, no extra features were enabled. This was just turning it on and off with default Fortnite. And the reason why I'm going to sort of kind of bringing that up is because, well, that meant that we now had more GPU time and more GPU load where we could potentially add more features in. So that takes us to, what did we add to this? So now we had something that we knew was going to help us with potentially thermals and battery life, but we wanted to see if we could take this thing and make it really add some more visual fidelity as well. So this first screen here is just Fortnite, the way we normally send it out of the box. No ASR, a screen res of about 75% on these dense pixel devices. And you can see it's a little meh, I'm sorry to say. It's got a lot of jaggies in there. The distance looks a little light, and shadow's not in a lot of places. The foliage up close looks pretty nice, but it doesn't go very far. There's not a lot of screen effects on for this particular run. But as we see here as we go, we're going to first, oops, I went too fast. The first one, let me drop back one. Sorry about that. I went a little too fast. So first we did is just turned ARM ASR on, kept the same screen resolution. And you'll already notice right away that it sort of cleaned up some of that jagginess, which is sort of the whole, hey, it can do TAA while it's added effect with this. But also, makes the game just look a little bit better over what we were seeing before. So that already is reducing some of our GPU load, but we figured let's try going a little bit lower. Oops, now I went backwards, sorry. There we go. Now we're going to a screen of 59% res, and you can notice that it doesn't really change over the 75% res, which is what we were hoping would be the case, giving us yet more GPU time to work with. I'll also point out that I've forgotten here that we were using the performance shader characteristic. There is a quality and a balanced version as well, which we do want to spend more time and actually play around with, because I do think that'll improve the visuals even more. So with the screen 59% and ARM ASR on, GPU load is down a bit. Let's see what we can turn on. So the first thing we enabled was more shadow cascades. And you can already see that there is a bit of more shadows down here. The distance actually got a little bit more shaded, darkened as well from the distance shadows that we turn on from that. And then from there, we turned on foliage density. Now, this mostly just changes the density in the front. You don't see any extra in the distance, but it is a bit denser, a bit more PC style on the foliage at this point. So now we're getting the densities of PC, we're getting sort of the shadows of console, maybe a little bit further into PC as well. And then, well, we just kind of turned everything on at once. And so now we kind of have a larger distance with distance culling. We've turned on a variety of post effects, including screen space reflections, ambient occlusion, some tone mapping, and quite frankly, now we have foliage going down the hill all the way down into the lake here. We've got a lot more visual fidelity in the scene in the back, or the city in the back, as we've now been able to render that data as well without having to distance cull it. So overall, a more visual rich screen to look at. So just to recap, before, after. And we'll kind of do it one more time, before and after. And so we've definitely improved the look. We've added the ability for users to see further, see more further. And it's also still all running at 60 frames per second. None of this has reduced the frame rate. In fact, ARM ASR has actually reduced our missed vertical sync to a third of what it was before, from about 24% down to about 8% at 60 frames per second. So clearly, we're seeing quite some benefit from ARM ASR being enabled in Fortnite itself. All right, so where are we going to go to next with this? So with this now enabled, that sort of leads us down the direction of some other possibilities for us for Fortnite. Enabling SM5 is one of the things we've been talking about even before this, but now this really becomes more of a feature that we want to go after. And that then enables the ability for us to start to bring more and more desktop features to Fortnite and the mobile platform, and make the artist's vision more similar across all the platforms that we support. The nice part about this is that what we have shown here will ship soon on Fortnite. In fact, it will ship in our release that is upcoming on select Android devices. And then a lot of the extra features that we've enabled will soon follow thereafter as we get a bit better testing across more of our devices. So I'm expecting the visuals of Fortnite to actually increase dramatically in the next 2 to 3 months. So that's a quick look at how ARM ASR is helping us push Fortnite further on mobile than ever before. But before I wrap up, I want to give a special thanks to the engineers who made this integration possible. Our rendering engineer, Brad Blankenship, did most of the integration work and found various optimizations that would help our rendering engine work well with the plugin. And then our optimization engineer, Dennis Cementiai, worked with Bruno Ferreira to do that landscape optimization that we just shown. Their efforts were essential in getting ASR running in Fortnite, and so I thank their efforts. It's been a fantastic collaboration with ARM, and we're very excited about what this unlocks, both now and down the road, and thanks with all that. I'll give it back to Peter.
Thanks so much.
Yeah.
This is the stuff that really makes my heart glad. We're talking about immediate results that benefited, in this case, the Fortnite team to crisp up their scenes, to offer elevated user experience, and it speaks to the road ahead. You know, Pete mentioned the SM5 renderer. And so, in a way, we're playing a small part in making the future happen faster. And that is exactly where I love being, and where it pays off in tangible results into the Unreal Engine. Well, isn't that a wonderful, wonderful outcome? And I would also add that, of course, they gave us product feedback. We helped Web kind of become better as a result of the feedback that they're going to give us upstream into our GitHub, and everyone can benefit from that. Excellent. So in these closing slides, what I'll do is I'll talk a little bit about how you can start taking benefit from ARM ASR yourselves, some hints on working practices, and then finally turn over the baton to you if you choose to pick it up. As mentioned, we got 3 presets, and you can choose to go immediately for the high quality end, where you were really working hard to maintain image quality. You can go for the middle of the roads, which we believe is quite a good compromise between image quality and resource demand. Or you can lean into performance, where we will make some trade-offs on image quality, but you'll get further benefits in terms of power draw and time saved on your GPU. These are all for you. We don't feel it's our place in this world to steer you towards any particular choice for your shipping decisions. But of course, you've got to start somewhere. So we suggest you start in the middle, see what you get out of it, and then adjust to suit. It's yours. As mentioned, this solution is platform agnostic. We want to make sure that you're getting as much benefit in your games as is humanly possible, that it's realistic for you to adopt. And so this feels productive for everybody. And so although we're proud to support officially Vulkan and Glez, you'll also find that it works very well under DX 11.12. And we know from other people who are using this, it runs just fine on Metal and other closed platforms. We recommend that you think about whether this is for you or you don't. ASR is not a silver bullet. It's great when you've got expensive pixels. And it's great when you have the performance there already within your device, which is so significantly, or devices that are modern enough for this particular tool and technology. So in other words, we're saying devices that come from, say, about 2022 onwards, these should be a pretty good fit. But you still have the rest of your audience to cater for, and you may find that you still want to use upscaling. And at that point, you may choose to use a cheaper spatial upscaler in order to hit your goals. Adjust to taste. And as mentioned earlier on in my first segment, we want to be here with you. We want to hear from you. We want to make sure that we're continuing to offer you genuinely useful tools, whether that's through ARM ASR, and you can find the links on the screen right now, or if you choose to engage with our performance tools, as Pete mentioned earlier, please get your hands on those, learn a little bit more about how to optimize your frames, help us learn how to serve you better. It's all there. Come visit us on our developer sites, because it's something that we're very proud to do, to see these practical outcomes where games ship, people take pleasure in playing the games, and we can feel that in some way we helped you deliver. And that takes me to the final slide, where I warn you I'm likely to gush, because thank you is too short a phrase. In order to get to this point here on the stage, we relied on so many people and the great work that they did. Whether we're talking about the foundations, which is, of course, with FSR2 and AMD, we're greatly appreciative that they took the stance they did and offered this technology to the world. Within my own team, this covers the fundamental optimization work that happened within our graphics teams, the proof of the pudding that came from our content team, the productization work that came from our XPK team, all the supporting mechanisms around it through developer education, through our legal team to get clearance for open source. So many people, alongside the partners that have chosen to engage, whether that happens to be Unreal Engine and especially Fortnite, or others such as Enduring Games and others around the world. It's been a wonderful journey. Let's keep it going, because it's the stuff that we really live for, and I hope that we're genuinely offering you that help. So thanks. So we do have a few minutes on the clock. If you'd like to, then by all means step up and ask either of us questions, and we'll do our best for you.
Yep.
Testing, testing. Testing, testing. Testing, testing. Quiet down, my darlings. We are about to start. Just a quick notice before we start. If you prefer not to watch my antics, you can get the text version over here, scan the QR code. It is live right now. Or you can just search for The Great Hitch Hunt, or get the link at ade.games. It is there near the top. For the rest of you, enjoy the show.
Hitches! There are hitches in our games!
Hitches? Can't be true.
Oh, they're real, all right.
Oh, yeah, we've seen them.
It's a real struggle.
Sounds like it's time for a hitch hunt.
There's hitches in our game.
Makes our players go insane.
We see all of them, it's true, which we'll note in our review.
We won't take it, everyone. The Great Hitch Hunt has just begun. Kill the hitch, fainters might make you sick. All these hitches, burn them down. No more raindrops in my town. Profile it, trace the pain. Hits engaged drive me insane. Scar the logsticks through the code. Find the frames with game that's load. If we channel all our might, we can get them out of sight. When no stutters will be had, makes the Foundry people glad. Now get ready for a fight. We will debug till it's right. Now all of you, kill the hitch, optimized and running rich, smooth like butter, keep it slick, locked at 60, renders quick, kill the hitch, when it's dead commit the fix, and we will not ship at all till we've killed every last hitch, kill the hitch, kill the hitch, kill the hitch. Hear ye, developers. A great scourge plagues our beloved industry. There are hitches in our games. And I don't know about you, but I'm sick of it. I say we kill them all. But I need your help. By the end of this presentation, all of you will also be hitch hunters. And as hitch hunters, we have but one goal. When I say, what are we going to do? You all say, kill the hitch. What are we going to do? Kill the hitch. What are we going to do? Kill the hitch. Kill the hitch. That is right. But one does not simply just kill the hitch. You need tools of the trade. First, we have the Lantern of Insights. This is no laughing matter. The Lantern of Insights allows you to see the hitch. Do not fire blindly into the darkness, for you will often miss. Next, you need the source of truth. It allows you to know why the hitch exists, and it can give clues on how to kill the hitch. Lastly, your weapon of choice. You know where the hitch is. You know why it exists. Now you figure out how to kill it and then go for the kill. The specific weapon and method will differ based on your needs. That was a lot of fun, but let's get real. Well, all of these steps were a metaphor for always using the what, why, and how workflow, the methodology. I have a methodology. I have a whole presentation about it called Maximizing Your Game's Performance in Unreal Engine. If you're watching this online, I actually recommend pausing this video and go and look at and watch this presentation, I consider it a prerequisite for this talk. But for the rest of you, basically, to summarize it, first, we always figure out what is slow. We see what is causing the slowdown in a profiler. Because if it is time-consuming, it will show up. Next, and only after the first step, we check why it is slow. And here we investigate, go by fact, check the source, don't guess. Ask people, go on Unreal Source, the Discord channel, use Epic Priority Pro Support, or formerly known as UDN. And then, as the last step, how do we fix it? And this is only with all the info we've gotten before. I see a lot of times developers, they see the game is slow. Oh, my game is slow. I'll just start fixing things. I'll optimize my meshes. I'll go turn on random checkboxes. That is not the way we do it. We measure, we investigate, and then we know exactly what is slow and why, and then we tune that. And I wish I could just say this, like, just do this, enter first station, bye. But still, games are hitching. And I think, well, because figuring out the why can be difficult and sometimes too late. Suboptimal workflows can compound to be hard to fix late in production. Some problems, they will not show on the profiler until it's too late. You've noticed you have death by 1,000 cuts, and you're 2 months away from launch, and you're like, we would have had to do the game differently. And like now we just have to mitigate. It's very punishing to first do things non-optimally and then have to fix them afterwards. Like if you use the what, why, and how, yeah, you fix them afterwards if you can, but I think it's better that I just tell you what are the most common sources of hitches in Unreal games on the market so that you can make your game properly from the get-go. So that's what this whole presentation is about. It's a list of the most common hitches. There's 7 of them that I managed to cram into this in 1 hour. No time for Q&A, sorry. And how to avoid them. But Ari, how did you figure out what are the most common hitches? Well, I actually interviewed 18 studios and code developers. Half of them were code developers that fix hitches for a living. Actually, I want to know how many people here were part of helping me with this presentation. Can you put your hands up? 1, 2, 3, 4, 5, 6, 7. At least 7 of you. And these are scary hitches. I'm going to show you a hitch. I'll tell you, this is the hitch. And I want you to sound terrified. I want you to just scream in terror. Oh my God! Put your hands in the air like, oh, cover your face. Because you cannot underestimate these hitches. If you're not scared of them, you're underestimating them. And then they can sneak into your games. So we have to do this properly. So the first hitch on my list of hitches, very, very common. And remember, I want you to react. As soon as I say, you all go like, oh my God. Are you ready? It is the level streaming hitch. You should be scared. That was the proper reaction. And the funny thing about the level streaming hitch is that this is actually the only hitch that is kind of like, it's a family of hitches. It's like, it's a group of issues. Every single hitch in this presentation can happen during level streaming. So it's kind of like a, I don't know, it's not a real hitch, but it kind of is. A lot of things happen during level streaming. But there's one thing you can do during level streaming that will like make these hitches worse, and that is using actors for static geometry. You have environmental artists, you have designers, you have level dressers, all of these people, and they want to put down lots of static meshes. So what they do is, of course, they drag them in. What else can they do? They put a table, they put cutlery on the board, they put glasses, they could put a bookcase and books and everything like that. Of course. So they put down lots of static mesh actors. And this can work for small games and levels. If you're working on a small game, small level, and you're watching this, and you're like, oh, I'm not supposed to do that, don't worry. It's probably not going to show up on the profile for you. But if you're working on dense, big worlds, or a AAA game that has a lot of this, or an indie game that does have a lot of stuff in it, it's actually horrible. It's horrible for dense and or large worlds. So your outliners should not look like that at runtime. So why shouldn't you use static mesh actors? The thing is, actors have overhead to them. You have to load them in memory. The garbage collector needs to scan them. Actors are very versatile and like to do cool stuff with objects at runtime. But many times, you just want to put down a rock. And the only thing that rock is supposed to do is look like a rock. And you load in the level, the rock is there. You load out the level, the rock is gone. They're truly static actors, like true to the word static. They're immutable, dumb, they don't do anything. So you don't really need that versatility. And if you don't need that versatility, you should avoid using actors. So what can you do about this? You should avoid using actors for truly static geometry. Instead, there's plenty of things you can do. You can, for example, use packed level actors. They allow a non-destructive workflow. And by non-destructive, I mean like you can still put in all your static mesh actors, like because it's a fine workflow. And then you put them all in a level instance, and then you can export it into one single actor that has a static mesh, instant static mesh component for each unique static mesh. This is a bit manual workflow, and you have to be careful not to have the actor be too large so that it spans multiple tiles, or not have it too small that you're still putting down too many of them. But this is usually what we recommend people do first. Then procedural content generation. It automatically creates a single actor per cell with static mesh components. You can still create, like, put all your static mesh actors down, again, convert it to a level, and then you can convert that to like a data asset that the PCT can sample from. And then only one actor per cell with static mesh components for each unique static mesh. Let's say also you're a tech artist or programmer or scripter, and you have tools for like scattering around static meshes in your scene. Those tools should be using instant static meshes, not just static mesh actors. And if you're using landscape and putting foliage on it, like grass, pebbles, flowers, anything like that, we actually have a tool called the foliage tool that will automatically put all the stuff into ISMs. Or even Mass or Niagara, if the use case calls for it. For example, if you have lots of leaves and you want them to move, like, hey, maybe this could be Niagara. Or with Mass, you could have, like, you want to simulate a lot of things, but when it's super far away, you don't even want to show it. You just want to keep it in Mass in simulation. When it comes a little bit closer, you put it into an instant static mesh. And when it comes even closer, you hydrate it to a full actor. And then also with PCG, you can even do the runtime PCG GPU scattering. But that's a lot of things you can do it. But what are we doing about it? Well, we want you to be able to keep using the workflow where you put static mesh actors into the world, but at runtime, it doesn't incur the overhead. So we have something called cell transformers, and this is only for world partition maps. What a cell transformer does is that it loops over all actor of each world partition cell. It will do some action on it. It does this both for Pi and for cooked builds. So you can test it. It's not going to break only in cooked builds. It's going to be a nightmare to debug. No. It's going to break equally on both. And you can make your own, but we also provide one that transforms static mesh actors automatically into static meshes. And you can see that's like allow classes and disallow classes, and you can change it to be like your own actors. You have to be a little bit careful with it though, because the static mesh actors will not exist at runtime. They will just be instances instead. So like if you were planning on like referencing them or something like that, you know, that's like, oh, what are you going to do now? This is experimental in 5.5 and also in 5.6 that just came out. But like when it comes to like different experimental levels, like this one is only at like editor and cook time. It's not really that much at runtime, because at runtime it's just a static mesh actor. So when it comes to experimental, some say like, you know, you can experiment with this one. Of course, officially I will say don't shit with this, but unofficially I'll say, but I'm not your mother. We're also just working generally on streaming performance improvements like you saw during the State of Unreal. In 5.6, we introduced many of them. Although they are experimental, we haven't turned them on by default yet. But don't worry, we will turn them on by default once they're ready. So you don't have to go like, oh no, I forgot to turn on something in an update and now my world is slow. No, like as soon as it's ready, it'll be enabled by default. Like for example, async component registration, physics state creation and destruction, and a unified budget for async loading and level streaming. Those used to be like two separate ones, or sometimes they would stack. Now it's one single budget. You can also, of course, you know, play with it, turn it on, see how it works for you. But those are runtime, so like be a little bit more careful with those. We also just introduced the fast geometry streaming plugin. There's a great presentation about that from Richard Malo from Epic Games and Jaroslav Rutsky from CDPR. Called Streaming Improvements from the Witcher 4 Unreal Engine 5 Tech Demo, something like that. You'll find it on yesterday's live stream. So definitely check that one out. It basically, all these actors, it will just not even go to U objects. It will just create structs for them. So it's a really good talk. Sorry, like they just announced it like yesterday, so I don't have a link to it. But it will be in the written version of the article that is on Art.games once I have time to put it there. Okay, Remember what we're going to do as Hitch hunters when we know what to do? So we know what to do. What are we going to do? Okay, let's try once more. What are we going to do? The Hitch is dead. Oh, but the lantern sees more. And this is a scary Hitch. So remember to react accordingly. It is the physics Hitch! Ooh, that's a scary one. So the physics Hitch, what's the problem? Content teams not optimizing their messages for physics. That is the problem. And I think maybe one thing that made this problem even worse, that when we introduced Nanite, and we were like, you can put whatever you want into the world, and it's going to render beautifully. And we're like, it renders well, but for the physics, it's never worked like that for physics. You always have to be kind of careful of how you author your physics world. And Nanite basically went put everything, every single rock, make it high detailed, and yeah, we need to reconsider a little bit the physics side of it. So the problem is if you have a big or complex physics scene, it will slow down physics simulations, it will bloat memory, and it will increase loading times. So if you have also, for example, the smallest loading unit, incremental loading unit during level streaming is one single component. And if you have an instance static mesh component with a really complicated physics object with thousands of instances, that's just going to hitch. So what can you do about it? Well, you need to optimize your physics. Static meshes have both simple and complex physics in Unreal by default. You don't have to do it like that. It's not like a requirement that you have to make both. The simple physics are used for the physics simulations when they collide and stuff like that. And the complex physics are for you when you want to trace against it. And you should use simple physics wherever you can. So if you don't need complex physics, just turn them off. I actually recommend for your projects to set the use simple as complex project-wide setting if you can, and only override it when you need it on a per mesh basis. If you toggle this late in your project, all the current assets still have the old ones, so you'd have to go through them, just create an editor utility bit or something to do that. But yeah, if you can do this, definitely do that. You should prefer in order for the simple physics, spheres. They are the fastest, then capsules, then box, then convex polygons, with these trash bins in the city demo. Here you can see on the left, the one is good, it's just a capsule, super fast. And then you have the polygons. Even though it looks like it has fewer edges, it's worse. We have to check against every surface. And then the worst is on the right, it just has horrible physics, it's just too much, and you don't need this really. And I know as an artist, you might think sphere is the most performant? That makes no sense. Programmers have been slapping my hands because I keep putting in all these perfect spheres that have infinite amount of vertices. But the thing is, in physics, we're just using math if we can. And a sphere is just a location and a radius. And figuring out if two spheres are intersecting, you just get the distance between them and subtract the radius of both. And that's it. It's super fast. And actually, there is one even faster shape than all of these. And that is no physics at all. If you have a lot of things in the distance, there's some vista there and the user is never supposed to be able to interact with them, don't even have physics on that object. Just completely remove it. You should also set up proper collision channels. So have the objects only collide or overlap with other objects that are actually relevant to it at the physics level, not when you check for collisions. And I actually recommend you watch this video. It's called Collision Data in Unreal Engine 5, Practical Tips for Managing Collision Settings and Queries. This is a really good talk. This was made by Studio Gobo for their work on Hogwarts Legacy, which shipped on Switch 1, I might say. So definitely check this out. Have everyone in your team that has anything to do with placing anything in your level, or any programmers, or basically anyone that has anything to do with optimization or content in your game, watch this presentation. You should also disable unnecessary overlaps. Whenever an object moves, it checks for overlaps. And this is for you. This is not for us. We don't need the overlaps. It's if you want to react to it. If you're not reacting to overlaps, turn them off. There's a per component setting called Generate Overlap Events over there. And you can just turn it off. It is on by default, because we don't want people to add a listener and have it not work. But they can get very expensive. So, so that means that, actually, I've seen some studios just go to the primitive components constructor and just turn this to false by default, and then only enable it when they actually need. And like that's an engine modification I would recommend to do. If you need overlaps, maybe you don't need overlaps when the level is being streamed in, so you can skip updating the overlaps during that time. Every non-static object will check for initial overlap when it's being streamed in. And this is often unnecessary. Like you're authoring that level, you know that no object is going to be touching your volume or something like that. So I would recommend just first of all set mobility to static on objects that don't move, and then like we know that they don't move, so we don't need to check for overlaps. Or you can turn off overlaps during streaming. There's this config variable, default update overlaps method during level streaming, and it's by default only update movable. And I would recommend putting it to never update for all the actors, and then only override it if for some levels where you're like, okay, this volume actually does need to check for overlaps when it streams in. Then you can override it like that per actor. You should also optimize your overlaps, again, if you need them. If you need overlap updates, make sure it only overlaps with the object types that you actually need. For example, instead of overlapping with everything and then in the on-overlap event cast to the player character to see if you overlapped with them, just have it only be able to overlap with the player character. It makes the physics simulation so much easier. Again, watch this video, it's great. You should also reduce the physics scene size. Only load in the meshes that you need. Use 8 slots for the rest. An 8 slot is when you take a lot of actors and you throw them out and you replace them with one big actor that might not even have collisions on it. And with world partition, we already have this kind of working automatically, and you can adjust it with loading radius. Or if you're using the classic level streaming, like sublevels, you should still cut up your levels into units, chunks, to make sure that you can keep your physics scene small. Also, if you're using world partition, be mindful of the amount of persistent objects. Some further optimizations you can do is, for example, using the editor view modes and Chaos Visual Debugger to find issues. How many people here have ever opened the Chaos Visual Debugger? Can I see some hands? So about like 15% of us. I would like this to be way more. This is a new tool. It is amazingly powerful. You can start it right from the editors, like in Tools, Chaos Visual Debugger. And it allows you to record the entire physics representation of your game for like a span of time. And then you can see every single context and query and everything. And your physics representation of the world should be very simple. It should be optimized and not have any like unnecessary thing. Like I should not see every single stone there. It should just be flat. So definitely, like if you see chaos on your profiler, don't go like, chaos is slow. Go check on Chaos Visual Debugger because you might just have way too much physics. You should also use physics proxies. Do you have like a convenience store and there's a box full of fruits there? Or do you have a library and you have a bookcase full of books? Every book should maybe not, like can the player even interact with every single book? Can the player lift those fruits? If not, turn off the collisions for them and replace it with one bigger physics proxy. We just call it physics proxy when you do this. It's not a specific thing called the physics proxy. It's just like this practice is called doing a physics proxy. Also, if you're doing traces and you're noticing you're doing too many of them and they're too slow, then of course, you should just make sure you're not doing too many of them. But you can also turn them into asynchronous traces. This is only possible in C++ currently. But what it does is that it delays the result to the next frame. It does the traces during a time where they're actually more optimized. And just remember that I feel like this is a band-aid, just reducing the physics scene size and the complexity, or just doing fewer traces. It will all like make the traces faster and make your game faster. So yeah. But what are we doing about it? There's a lot of things that you can do. What are we doing? Well, we are working on async physics initialization. It moves the physics initialization and destruction off the game thread, so it's all on the worker threads. This is currently in an experimental in 5.5 and 5.6. You can try it out, but don't shit with it. But I'm not your mom. We will enable it by default once it's ready. Until then, you can test it with these. And we don't recommend shipping with this yet, again, but remember, if you have a too large or complex physics scene, it will still be a problem. This will make noticing those harder. Like nowadays, when you have like a horribly optimized physics world, it might show up in the profiler and someone will go like, I need to look into this. Oh, team, we need to optimize. This is gonna, sure, make it not hit, and then the physics scene will grow and bloat and become horribly unoptimized. And you're not gonna see it until everything in physics becomes slow. And then people are going to come to me and say, Ari, chaos is slow. And I'm like, no, your physics scene sucks. We're also doing general chaos improvements in 5.6. We did better multi-threading. We made it a bit more data-oriented. We did some speed improvements. Sorry, I'm going fast through this. I have not that much time. And other chaos improvements for future work is that we're just making it even more multi-threaded, improving the task graph utilization. I think I heard someone say that this island partial sleeping is already in 5.6, but yeah, optimizing the sleeping, and also we just keep making chaos faster and better. We didn't just ship it and say like, good enough. No, we know we can be better improving, and we are working on making it better improving. So now that we know what we have to do, what are we gonna do? The Hitch is dead! Yeah! Oh, but the lantern sees more. And this is a scary Hitch. Remember, the next Hitch is the actor spawning Hitch! It's a scary Hitch. So, what's the problem? Actor spawning, it actually needs to complete the frame it's initialized. And not just the frame, the line of code that you do it. It needs to be ready for the next line where you actually want to use it. And also for Blueprint, you spawn the actor, you need to be able to use it in the next node. This is unlike streamed actors, because they use incremental component registration, so they can take many frames to initialize. We don't have the luxury for instantiating actors. And if you have very expensive actors, like characters, NPCs, they can take many milliseconds to spawn. And if you have many of them, they can hitch. So what can you do about it? Well, you need to simplify the actors you're spawning. Just do less, have fewer components, have them do less work if you can. Also, you should, if that's not enough, you should limit the number of actors you spawn dynamically each frame. When I was doing the interviews, many studios actually said, especially for limited platforms like mobile or Switch 1, they had a limiter where it only does one actor per frame for very complex ones like characters. So definitely check out that. Also, you should delay the initialization of components where you can if it does need to happen, but maybe not immediately. For example, skeletal animations, they can be initialized later off the game thread via the tick animation on skeletal mesh init project setting. Like animations, they usually happen on ticks asynchronously on threads, but when you're spawning it, we assume you need the correct pose in the next line where you're actually going to use it. And if you don't need that, you can just have it do it during the next frame's tick. But it will show like the default pose while that is, between that is happening. But usually you're spawning actors off the camera anyways, right? So just hide it for that one frame and then show it, like, yeah. You should also consider pooling actors where it makes sense and where you can. It's quite easy, just like instead of like always creating a new actor and then destroying it, create an actor, and when you're supposed to destroy it, just hide it. And then when you need a new actor, just show it again and like reset it. So what are we doing about it? I have heard many people asking me like, oh, when is Unreal going to implement actor pooling in Unreal Engine? And the thing is, it's a very hard problem to do that fits every single type of actor currently and future actors for every single game type, for every single project type, for every single industry, and every future, all of these. It's a very hard problem. We've looked into it, and it's just like, oh, this is a horrible mess. It's so much easier for you to just create a pool per actor that you needed. Oh, for the bullets, yeah, or projectiles, I'll make one actor pool. And for this kind of enemy, I'll make one actor pool. It's super simple because you know exactly what you need to initialize and reset every time. So because of that, don't hold your breath for anything from us. Like if anything, like scene graph in like way future is going to make it a lot easier for us. But you just do it yourself until then. Okay, Hitch Hunters, now that we know what we're going to do, what are we going to do? The Hitch is dead! Yay! But the lantern sees more. And this is actually a Hitch that scares me a lot. And it should scare you too. It is the dreaded piezo compilation Hitch! I don't think you grasp the seriousness of the situation. I said, it's the piezo compilation Hitch! Yes, be scared. You were only alarmed. So what's the problem? So when DirectX came out and then Vulkan and Metal, they have a new way of dispatching draw calls. The complete pipeline state object is now needed at the time an object needs to render. But this is actually good. This is amazing. This allows great performance and parallelization opportunities. We managed to completely refactor the render hardware interface thread because of this. But the PSOs also need to include the fully compiled shader code. And there's like, for consoles that we know the GPU, we can just do it while we're cooking the game for the user. There you go, it's all ready. But on PC and mobile, there's so many different graphics cards and driver versions and everything like that. We can't compile for all of them. This is going to be terabytes or even more of data that we're shipping to the users. So we have to compile them on the user's device. And this was maybe okay at first when DirectX 12 was introduced, but with how complicated shaders have gotten, shaders now take a while to compile. So do not take forever. You don't want to compile every single permutation of every single shader in your whole project on the user's device. They would just take forever and you would fill the hard drive. So games only compile the possible PSOs the user might actually see. And this is usually compiled during an initial compiling screen. It will say like, oh, we're compiling shaders. It takes 10 minutes. The user will be like, as long as I don't have to hit during the game. And when you're doing it this way, in Unreal terms, we call this bundling a PSO cache. And this is the old way of doing things. But the thing is, figuring out which PSOs the user might see, it's a very difficult, it's a time-consuming and imperfect process because, like, what do you have to do? You have to play through the game. Look at everything, look at every permutation of everything, and pray that you saw everything, because if it doesn't, it's going to hitch for the user. Well, I mean, it's possible, but like for linear games, easy. For dynamic games, harder. For open worlds, very hard. For procedural games, like roguelikes, oh my God, so difficult. For user-generated content games, impossible. And yeah, they will hit if the PSO hasn't been compiled by the time of the draw call. And it's just, it's very tedious. It's like you have to, just automating or playing through. So when it happens, when those hitches happen, it's called the shader compilation stutter. This is what the industry has been talking about. This is why, you know, all these reviewers online are saying, oh, this is horrible, oh, this stutters, everything. It's this. We have a new tech in Unreal called PSO precaching. That is not the same as bundle PSO cache. We have those two technologies working in Unreal. And it was enabled in Unreal 5.3 by default and introduced. And what it does is that instead of you compiling all, or collecting all the PSOs and compiling them on the user's device, you don't have to do any of that. Just when we're loading in the level or loading in assets, Unreal will just automatically compile all the possible PSOs that that object might need, and the loading will just take a little bit longer. It will be all asynchronous. No hitches anymore. Oh, amazing. But what can you do about it? You need to have a PSO compilation strategy. When I first started looking into these PSOs, I was like, oh, I need to add a few slides about this. And I started looking into it, and it's like, it turned into a major rabbit hole. I was like, what is this? Why isn't there more information about this online? And it turned into a month of research. And I was like interviewing companies, like I had a call with NVIDIA and Microsoft. I was like, what are we supposed to do? And I was talking to my rendering director and rendering engineers. And I was like, what are we doing? What's happening? And we actually have an entire hour presentation. It turned into an hour presentation. It's right there. It's called Game Engines and Shader Stuttering Unreal Engine Solution. You can check it out. There's also going to be a link at the text version on ara.games. There's also a blog post by the rendering team that this article references. But yeah, to summarize, any game releasing on PC or mobile, on the new graphics APIs, you need to have a PSO strategy. It used to be, I'm just going to make a game, and then you ship it. No, now you need to make a game and have a PSO compilation strategy for your game. That's how making games today is. And this hasn't been messaged clearly enough to game developers. I didn't know this until it became a problem. And I work for Epic. It's like, you know, like every negative reviewer is like, oh, compilation stutters. And I'm like, why is this? Like PSOs, what the hell is that? Now I'm doing mine to make sure you all are aware of it. So what are you supposed to do? If you're using Unreal 5.2 or older, then you need to set up a bundled PSO cache for your game, period. It's going to suck. You have to play through the game. You have to put automated playtests. You have to collect all of them. And it's going to be tedious, and you're going to hate yourself. And then if you miss some, then you're going to have hitches. And people are going to say, your game is a stuttering mess. And then they're going to call us our engine Stutter Engine. And it's not, it's just like, it's a very hard problem. We're trying our best. Stop being so mean to us. We really want your games to perform. And if you don't have a bundle at all, it's going to be a hitching mess. if you are using 5.3. And later, though, we have piezo precaching enabled by default. It's not fully effortless, though. You do need to have an initial loading screen while compiling the global shaders. Those are the shaders that aren't tied to the lifetime of an object. Like, for example, when we're loading in an object, we know, oh, this object has those shaders. But compute shaders and post-process shaders, like we don't, we have to do them at the start. Unreal will automatically kick them off, but you need to have a little bit of an initial loading screen, like, hey, Unreal is still compiling its initial shaders. There's this variable called none precompiles remaining. You have to wait until that turns 0. And for Blueprint games, we do have a Blueprint version of this variable available in 5.6. Sorry that didn't come earlier, but it's very easy to expose to Blueprints. It's a single line. You can just make a one-line function around it. It's not free, though. It's not a silver bullet. We want it to be one, but it's close. It's as close as we can get. It does use CPU cores at runtime to compile, which is not an issue with loading screens. Like if you have a loading screen, the loading screen just takes a little longer. Oh no, just for the first time, by the way, then it's cached. But if you're streaming in levels for the first time you're playing the game, the streaming is going to take a little bit longer, and it's going to saturate the CPU cores, which might compete with other systems that we're also going wide on, like the animation systems and anything else. You might think, can't I use both? Can't I just put bundle piezo cache and then have piezo precaching catch the one that it doesn't catch? It doesn't really work like that, because piezo precaching, it happens earlier. It happens at the time of loading, and then the bundle piezo cache, we only fetch that when we are dispatching the draw call. So piezo precaching, because we don't know how it's, for example, how your object is going to be lit. Are we going to use directional light? That has its own PSO for its shadow pass. Are you going to use a point light? Or like any other type of lights? Like they all have their own pass, their own shader, their own PSO. So with piezo precaching, we don't know how your object is going to be lit, so we just compile all of them. But for bundle piezo cache, you know exactly what situations your object, how it's going to be lit. So how it's going to work is that piezo precaching usually compiles like 3 to 5 times more shader permutations than you're actually going to use. And if you also use it with a bundle piezo cache, it will reduce that by a bit. So instead of being 3 to 5, it will be 2 to 4 times more. So might not be worth it. You decide. You also need to test it and profile it. Because when we were doing this, us game developers, we were, oh, DirectX 12, what's that? That's cool. Okay, let me test my game. Oh, it stutters a lot. I wonder why. Let's try it again. Doesn't stutter anymore. It fixed itself. That was the driver caching the PSOs. So no wonder we were missing it. So every time you profile your game, I recommend you should start it with a clear PSO driver cache command line argument. And actually, I hate giving advice like that. It sounds very impractical. So I just made a plugin for this presentation. You're welcome. It's called the PSO Cache Buster plugin. It will automatically clear the PSO cache for all non-editor and non-shipping builds. So even if you accidentally keep it on while shipping, the shipping build will not do it. But test builds will do it. You can edit it to also not happen to test builds. Did I even add a CVAR for that? No, it was for the shipping builds. Make a pull request. Anyways. QA should only be testing the game in this way, in my opinion. And also profiling, you should only be profiling this way. And also, if you do have a hitch, like an actual hitch with piezo precaching, that's not supposed to happen, but you turn on validation equals 2, and then it will log the cache misses. So there's a lot of work that you can do. What are we doing about it? Well, we keep working on piezo precaching. It keeps getting improved. It received a lot of updates, and as of 5.5, we've caught all code paths in our own sample projects and Fortnite. There are no PSO hitches there for any of them. We're currently improving world partition H-slot support. I think that was already in 5.6, where there was a couple of frames where H-slots were hidden while we were compiling it, but now we compile them in advance. They're still not stuttering, but now it's even more seamless. And if you are doing something that maybe we didn't catch in our games, but maybe you have, just notify us through Epic Pro support or on the forums, and notify us so we can fix it. All right, now that we know what we're going to do, what will we do? The Hitch is dead! Oh, but the lantern sees more. That is a scary Hitch. It is the garbage collection Hitch. Ooh. So, what's the problem? Garbage collection needs to happen every minute or so to clean up unused U objects in memory. Every minute and also on every hard level change. And when you have too many U objects, the garbage collector can take long enough that it will hitch. So what can you do about it? You need to reduce the work the garbage collector needs to do. Reduce your U object count. That is advice number 1. Static mesh actors can be a pain point. That's another reason why you should get rid of them. Also, use world partition or level streaming to only load sections around the player so you don't have too many things in memory. If you do notice that the garbage collector is taking too long and you want to figure out why, you can use this command, obj for object, list dash count sort. And it will list all your U objects in the log, sorted, grouped by the class, sorted by how many they are. And I often get the question, Arya, how many is too many? Like, how many should we strive to have? I usually say like under half a mil is good, like 100,000, 200,000, fine. 3, 4, 5, getting more than that, you should like maybe start reducing them. If you're over like 1 million, 2 million, or even more, oh, you're doing something wrong. But also, this advice might not be future-proof. We might make improvements to the garbage collector. We might get better hardware. Many reasons we might have more systems that don't even use this anymore. So just be sure to profile and make sure that, garbage collector, if it's taking 1 millisecond in your frame, great, fine, whatever. 2 milliseconds, maybe we won't do other systems during the frame. 10 milliseconds, maybe we should start looking into it. More than the frame time, you need to reduce your U object count. If you're creating a lot of short-lived U objects, consider pooling them. Like, for example, if you're creating new objects with a new object function, then instead of creating a new one and then throw it away just for the garbage collector to pick it up and for you to spawn more, instead just reuse it. And also, if a lot of your U objects that you create like custom, then if they share the same lifetime, consider putting them in a garbage collection cluster. You can also, if the garbage collector is too slow and you're like, I can't do anything about it, maybe consider running it at strategic times, because you can trigger it manually at any time, and they'll give you it will reset the time. You can get 1 minute again. Are there any loading screens? Are there any fade to blacks? Are there any UI pop-ups or other still screens where the user isn't going to notice it? You can trigger the garbage collector then, and then, okay, we bought ourselves another minute. If you want to go quite hardcore, like for example, if you have a round-based game with small levels, you can run the garbage collector between rounds, but just make sure the U object spawning count per round is under control. You really need to be sure that you're not spawning too many U objects. So if it's always fixed, you can just say, don't run a garbage collector. I know what I'm doing. And then at the end of the round, okay, let's get rid of it all. And if you're having it on some device that has limited platform and it's running out of memory, we will notice it and we'll force run the garbage collector for you. So what are we doing about it? Well, okay, so regarding the reachability analysis, that's the mark and sweep states of the garbage collector. Most of the phases of the garbage collector are already incremental. The reachability analysis is not. If there are too many U objects, it will just take too long to scan them and they will hitch. So we are working on incremental reachability analysis. And this is highly experimental as of Unreal 5.5. Don't use it, please. Because often I say experimental, but I'm not your mom. Here I'm going to be your mom. Don't use it. Because we only are using it within Epic for single-threaded servers. So it's not multi-thread safe. Like the client is multi-threaded. So it doesn't really work for the client yet. But we do have interest in making it work for the client also. But even if it were working, and even if you're like, hey, I'm going to turn it on, that's still only spreading the work over multiple frames, cutting into your budget every single frame. So your primary fix should still be to just reduce the work the garbage collector needs to do every frame. All right, Hitch Hunters, now that we know, what are we going to do? The Hitch is dead! Oh. But the lantern sees more. This is actually one of the scarier hitches because of how long it can get. Be ready, react accordingly. It is the synchronous loading hitch! It's very long. So what's the problem? In Unreal, you can load assets either synchronously or asynchronously, or blocking is what we call it when you do it synchronously. And blocking load, it will stall the game thread until the asset is loading. This is the source of the longest hitches in Unreal. If you ever are playing a game, your own game, and you notice it's hitching for like hundreds of milliseconds, maybe up to a second, it is almost certainly this. Not always, but almost certainly. because it also flushes the asynchronous loading queue, potentially making the hitch so much worse. And why is this happening? Well, asynchronous loading, which is the better one, where you just say, Unreal, load this asset for me, and then tell me when it's ready. And Unreal says, OK, be right back. And you mind your own business. Then Unreal comes like, it's ready now. And you're like, ah. It can be more complicated because like sometimes in gameplay recursion objects right now, let's say I have a treasure chest, and I have a huge array of soft references. And I need to like load one of them and show it to the user. But the user just clicked the test, so I need to show it immediately. Someone who is a junior or maybe a non-programmer might just go with the blocking code because it's more easy. In the next node, in the next line of code, they can immediately start using it and like put it in the UI and whatever. Someone who's more experienced might go like, oh, that chest, I can already decide what the user gets out of that chest when the user is like 10 meters away. And then if I then I start loading it, and then when I get close to it, it's probably done loading. If it's not, I'll slow down the claim animation. And once I touch the chest, maybe if it hasn't loaded by then even, I'll show some smoke effects until it's done loading. And the player character will go like, whoa, until it's done. The thing is, all of this is extra work. So someone might just take a shortcut or might not know any better and then use the blocking loading function. So what can you do about it? Don't do blocking loads. Please don't use it. Don't do them in your game. You should use the async version instead always. And as I was talking to studios, many studios forbid them. They use asset validators to warn about them, or even they just remove them from the engine, the blueprint versions. They're like, you content team, you can't even do it anymore. And I know it sucks to hear someone say like, oh, just write a validator. You don't know how to write a validator for that, so I just made one for you. I put it into my common validators plugin that includes a validator for catching blocking load blueprint nodes, and it's in that. If you feel like you have any good ideas for additional validators, you can put them in or give me a pull request. Also, you just need to teach your team proper asynchronous loading workflows. What are we doing about it, though? Well, we are already informing the user. It's called load class asset blocking. And the tooltip says it will hit. It's like, don't use this function, it will hit. Don't do it. And then people are doing it. And I'm like, no. But if one of them sneaks through, like we have implemented partial flushing of the async loading queue. So it's less punishing. And it will still flush at least the current asset being loaded, and maybe the next asset, or any other asset that it depends on. We have it at least since 5.5. I didn't check exactly when we put it in. Maybe in 5.4. Anyways, it doesn't really matter because you just shouldn't do it. You're like, don't rely on this. Just don't do blocking loads. So now that we know what to do, Hitch hunters, what do we do?
Kill the hitch.
The hitch is dead.
Yay!
Oh. The lantern sees more. It sees one more. But this hitch is probably the scariest of them all, because this hitch is coming from within the house. It's in your own studio. It is your own blueprint and content hitch. Excellent. So what's the problem? Hey, you are doing too much. You have too many or too heavy ticks. You're doing too much in begin play. You have too many timers running. You're doing too much in response to events firing. You have too many sequences or too busy sequences. You have too many audio components, too many skeletal components, too many animators. You're doing too much of anything, anywhere. Okay, so what can you do about it? You need to do less. Profile, see what's happening, fake things if you want. Fake as many things as you can. Everything doesn't need to tick every frame, especially far away and hidden things. The user won't notice. It's video games. It's all fake. Lot things, level of detail. For example, use H lots where you replace all these actors with one simple one. Only keep close things loaded. But the thing is, when I say level of detail, many people think, oh, it's static meshes. No, everything, not just meshes. AI behaviors when they go further away, simplify them. Audio, when it goes further away, remove them. Particles, when they go further away, simplify them or remove them. You should do less so that you can put in more. You can quote me on that. I thought it was clever. And spread things out. Spread out the ticks. Make far hidden objects tick rarer. You should check out the significance manager. It allows you to assign a significance to something, and then you can decide how to react to it. Like, for example, switching to another behavior class, or lot, or ticking if you're anything. Like, it's all up to you. Begin play calls are actually already incremental for streamed-in levels, and you can customize it with these variables. End play calls are not, but usually people aren't doing much in end play anyways, but if you do need them to be incremental, I'm not going to say that out loud, but there's a very long okay, I'll say it. Level streaming, route actor, end play for remove from world granularity. What are we doing about it? For your stuff? Hey, this one is on you. But we're helping you with Unreal Insights. We're constantly improving it to make it easier for teams to find issues with their content. And recent improvements include the ability to mark regions, take screenshots in both Blueprint and C++, and just better editor usability. Like you can see there, you have the trace button already in Unreal Editor. Anyone can click it, anyone can start a trace, anyone should do it. Now that we know the last hits, Hitch Hunters, what are we gonna do? The last hits is dead! Wow! Good job, everyone. Good job. Having said that, there are more types of hitches. Like there's some of them that I couldn't fit in this because I am almost out of time. Are like animation hitches, UI hitches, and cloth chaos physics hitches. Hopefully those should make the most common hitches a thing of the past for all future games. But also we do need to have a bit of a reality check before I finish this off. A little bit, we need to talk, developers. There are limits in game dev. I've noticed a little bit of trend where we're kind of acting like it's not. Like, sure, we're not making games for the Commodores of yore, but even though the limits are much higher, there are still limits. They never went away. They're much higher. We can do a lot of things, but still there's a limit. And we have to respect those limits. For example, dense environments, they're hard. I remember when Crysis came out. Oh my God, Lost Force, we'd never seen anything like that before. Can your computer run Crysis? Everyone said, because it was so demanding. It was a technical achievement. We are working on technology here at Epic Games constantly to make this easier. But for us, this is a huge problem. You might have seen it, State of Unreal, how much effort we put into it to make this easier. But still, you need to just take into account, like, hey, I can't just tell my team, just make a dense city, just make a dense forest, and think it's not going to be hard work. It's going to be hard work. Crowds, they're hard. They're so hard. I still remember when I played Assassin's Creed Unity. Amazing game. There was this humongous crowd there on the square. Each had different animations. They were all different from each other. A technical achievement. They had a DDC talk about how they made that crowd. It's open now for everyone. You should check it out. So, like, I don't want to see people say, oh, we put 100 metahumans in our game and it's slow. Unreal sucks. No. You were never able to do that. You needed to think about faking things, level of detail, all of these. This is like hard work. And sure, you saw in the Witcher demo that we had a big crowd, but this was a lot of work. And you need to put a lot of work into it also. So don't discount the amount of work that goes into it. Just like, respect the challenge, this is what I'm saying. I'm not saying don't do it. Don't do it dense environments. Don't not do dense environments. Sorry, don't quote me on that. I wanted to try it. Just, be aware of it. Do go for big crowds. Just be aware of it. A lot of words to say game development is hard. You need to keep performance in mind during the game's production. Also, remember that Unreal supports many different types of projects. And you need to tune it to your game's needs, because not just projects, industries. Fake everything you can. The more you fake, the more you can put into your game. Level of detail, everything you can. The less you do, the more you can put in your game. And remember, you should kill all the hitches, because when you do that, you are a hitch hunter. Congratulations, you have graduated. At the end of this talk, I want to get a graduation selfie with all of you. So I am going to say, hitch hunters, what are we going to do? And you all say, kill the hitch. Let me see if I can catch all of you. Yes, good. All right. Hitch hunters, what are we going to do?
Kill the hitch!
Kill the hitch! Wait. No, sorry, I have other people I want to thank first before you thank me. I want to thank everyone who helped me with this presentation. Please give me a golf clap while I thank them all. Thank you, CI Games, my coworkers at Epic Games, Bloober Team, and Tanglewood Games. Thank you so much, Assemble, Electric Square, Climax Studios, Respawn Entertainment, keep clapping, Double 11, Ninja 3, and Dreamlab. Thank you so much, Obsidian Entertainment, Flix Interactive, GSE Game World, Studio Gobo, Virtuous Godzilla, and Crow Team. All of these people and more, thank you so much for helping me with this presentation and allowing me to put your picture on my slides. Lastly, okay, thank you. There's one person that I want to thank the most. This person came all the way to Orlando to this talk to watch me rant for an hour about performance, or they're watching this online. It's all of you. Thank you so much for coming and wanting to make the game industry better for all of us, not just game developers. Thank you so much from me as a game developer, but mostly thank you from me as a gamer. You are helping make this game industry so much better. Thank you so much! Good afternoon, everyone. Thanks for coming along for the last session of today. It's great to be here at Unreal Fest in Orlando. Nice to be in the Sunshine State where it hasn't stopped raining for 3 days, so that's been lovely. For those of you that don't know me, my name is Jack Gullen. I'm a senior visualization specialist at McLaren. I work in our design team, and I work on a day-to-day basis working on our future cars. Like I say, it's great to be here. It's been a great festival so far, seeing all the latest developments that's been going on. What I do and what the team I work in do is basically we help to create the designers' visions into reality. A lot of that is based around Unreal, so a lot of the stuff we do is some still imagery, some cinematic renders, and then we get involved like things like virtual reality, car configurators, and like I say, a lot of that is done in Unreal, among other things, but it's great to kind of get up here and talk about what we do. Most of what we do in the design studio tends to be confidential, so it's nice to be able to show you some of the stuff we work on. Like I said, today we're going to do things a little bit differently. Normally we stand up here, we show some videos, we show some images, and we talk around the current cars. We're still going to do that, but we're actually going to cover some of the prototype stuff that we get onto in the design studio. So we're going to focus on stuff that we actually tried out one afternoon as an interesting little idea. Basically, some procedural worlds that we've worked on to basically help push on our visualization content. So, like I say, I'm lucky enough to be working for McLaren. I work at our McLaren Technology Center, or MTC. This isn't an AI image. We didn't ask ChatGPT to make us some new supervillain layer. This is actually where I get to work 5 days a week. And it's great here across, not only here and our other sites, working with teams such as not only design, HMI, our ergonomics teams, our aerodynamics guys, and various other departments, using lots of different technology and really all coming together to make new supercars. Now, what's great about that is Unreal is actually intertwined with a lot of different areas in the business. Like I say, today, we're going to focus on some of the ways we use it in the design studio. One of the other nice things about our office is we have our incredible boulevard. It's a great source of inspiration, great source for visualization as well. There's only this place in the world where you can see a McLaren F1, a P1, and a W1 all sitting alongside each other. We're basically seeing award-winning cars that are all there that we can use as references for Viz. They're also some of the fastest cars in the world, some of the most expensive cars in the world, but also some of the rarest things that you can find. We're incredibly fortunate at McLaren to have an incredible color, material, and finish team. They give us lots of interesting samples and really work with us to help push on our visualization. That's a great thing to be a part of, but there's nothing better than actually being able to get down and see the cars themselves, and that's a great source of inspiration for us. As we move further down the boulevard, we're really lucky to share the space with our Formula One team, and it's great to see them doing so well lately. One of the things you can see here, we have our McLaren 750S and our McLaren Artura sporting our livery that we created at the end of last year, and Unreal really helped us deliver that quickly. We had to create lots of different imagery of the cars so that the designers could create this livery, and then we could launch it. And like I say, Unreal really helped speed up that process for our rendering. As I mentioned, having the McLaren F1 team do so well recently has been great. The last time they won a Constructors' Championship was 1998 when Unreal Engine 1 just launched, so it's been a bit of a while. Hopefully it's not as long before the next one, and it's good to see the season starting so strong, so hopefully we'll see some more trophies on the boulevard soon. But as I mentioned, we're obviously here to talk about Unreal Engine and how we use it as part of the design studio. We've been using it for over a decade, UE. We use it for various different things. One of the things that we use it for is obviously virtual reality. So when the designers have a new sketch and we have some test data, we can drop it into a VR environment. We can walk around the car. We can see it in different scenarios, see it in different lighting conditions. And we do that on a daily basis so that we can evaluate new concepts. To support that, we also have our car configurators. These are in real time. You might have seen on our website, we have our configurator. We have a slightly different one for the design team based in-house. And what we do here is we add functionality and we add things at the request of the designers that they need to be able to evaluate things more clearly. That then lets them look at different data sets, swap out different things, different wheels, different materials, different assets. Basically lets them evaluate things as quickly as possible. And we also have our McLaren Special Operations team, and they do a lot of bespoke content. They do our customer liveries. The guys over at MSO also have their own configurator. And it's great that all these parts of the business can work together for our designs. Now, the last thing we look at is our research and development. So as part of the Viz team, we're obviously always trying to experiment with new ways we can influence the design process. So we work on lots of different things. Some of the recent things we've looked at with Unreal are megalights, substrate materials, and we've looked at metahumans a bit as well. And even some of the things we saw announced at the State of Unreal yesterday, so for example, nanite foliage is going to be incredibly useful for us, and we look forward to getting our hands on that. And with that in mind, essentially what we're going to talk about today is procedural content generation. Now, PCG has been around in Unreal for a while. Some of you might have used it, some of you might have not. What it allows us to do is essentially, with only a couple of assets, create vast amounts of environments. One of the main challenges of visualization, as some of you may know if you work in the automotive sector, is that if you're trying to make a perfect scene, it can take weeks or if not months to create assets from scratch if you want to get things absolutely perfect. Now, sometimes we need a way to evaluate a design in a couple of hours, and we want to be able to basically show it in a million different variations as possible. PCG is one way we can do that. So today we're going to talk about that and just see how we can basically do more with less. So one thing I should note, we're going to start this because some of you in the room may have not been new to Viz, you may be new to the automotive sector, so we're going to start this from the ground up. So we're very much going to show this from a beginner standpoint. So some of you may be familiar with this, but we wanted to make it so that everyone here can understand what's going on. So we're going to do a brief introduction to procedural content. From there, we're then going to take our McLaren W1 model and prep it for animation. So we'll get it ready in the control rig in UE 5.5. And then lastly, we'll bring it all together for PCG in Automotive Viz. And we'll show you how it can not only influence our car configurator, but our animations as well. So like I say, the two main things we're going to start with today, we're going to build a basic PCG volume. We'll just set it up a couple standard different forest environments so that you're good to go with our scene. And then we'll animate our W1 model, and we'll have it set up for our level sequences, so then we can build upon this and create some new content. So we'll start completely from the beginning, complete empty project, and we'll show you how we can make some standard PCG volumes. We'll go through this quite quickly for those of you that are familiar, just so you can guys get up to speed as well. So we've got a complete empty scene here. All we have is a basic landscape, grass material, and we're going to create a new PCG graph. And we'll open this up. And we'll very quickly just make our standard scene. So we're going to grab a landscape data node. So we need to access the landscape in the scene. And then we're going to access our surface sampler. Now, we get these two things so that we can tell the landscape how much content we want to spawn in a certain area. And then from here, we can actually dial this up and down so we can control how much content spawns in those volumes. We can also use a transform points node. This allowed us to give a little bit of variation to what's going on. So we can actually vary the assets that are spawning. So we can spawn 3D models in different rotations, different scales, different positions, and basically do more with less here. Just from this one simple node, we can spawn lots of random content. And lastly, we need our static mesh spawner. And this is where we basically tell it what 3D content we want to spawn in the scene. Once we have that set up, that is our basic setup. So I'll just recap that very quickly so you can see it on one slide. Super nice and simple. We're accessing our landscape data. We're getting our surface sampler node. Once we have that, we can control how much content is in basically the volume. We can then access our transform points node. This lets us vary the content in the scene. And then lastly, we have our static mesh spawner, where we can spawn in our content itself. So let's go back and do that just now. So jumping back here, we have our static mesh spawner, and then we're just going to add 2 new array elements. All we're going to do here is drop in 2 tree models. We've got these from the Fab Marketplace. They're free assets, so anyone can use them. So we're just going to drag and drop these in so that we're ready to create our volume in the scene. Now, once we've done that, we can then save this and then bring it back into our environment. So we'll just grab this here, and then we're good to go. So again, we'll just save this, and then we're just going to minimize this here. We'll just drag and drop our PCG graph we've just created, and now we have a random volume. And we can change the seed value on the right-hand side here, and essentially vary our content as much as we want, just by changing that number value. Just like video games, if you've played Minecraft, you get a different seed, you get a different world. Same procedure here. We've got a bit much content here, so we're just going to knock back how much is spawning per square meter, so we can see a little bit more of what's going on. And we'll probably reduce that a little bit further, just so we can see it a little more clearly. Cool. So we have our basic volume here, nice and simple, nothing too complex. We'll now just drag and drop one in we made earlier. So all we've done here is dialed it up a little bit more. We've added in 4 or 5 different tree models, some rocks, some ground debris, and all we've done is basically built on what we previously had. So we've just taken our blueprints, duplicated some of these and plugged in some more variables, changed the 3D content. And this lets us just basically vary the scene a lot more, gives us a little bit more control over what's going on. So just to have a quick look at that, all we've done is we've duplicated our surface sampler mode and then our static mesh spawner. By using these, we can then change out the assets, so we can control the rocks, we can control the ground debris. We don't have to use transform points every time. It's just a little bit handy if you want to have a bit more control. But that's really all there is to it, to a basic standard PCG volume. Now, you can add a lot more content here. There's been tons of sessions across Unreal Fest, and there's lots of resources online how you can do more. But we're going to come back to this in a second. But essentially, for now, we've got our volume, we've got our landscape, and everything's set up and good to go. So we've just duplicated our assets out 15 or 16 times, and we've got our forest environment that we can then use in our scene. One thing to note, obviously this content is procedural. It's constantly changing. We can randomize it as much as we want. But what if we find something we really like and we want to save it? Because the PCG stuff can be quite processor intensive. So what you can actually do is if you basically select all the volumes in the scene, you can then come down here and select our clear PCG link button, and this will convert it all to actors. And that means it's not going to randomize anymore. So if you've got an environment you really like, you can then save this, keep it. When you reload the level, everything's good to go. Now, for today, I mentioned this is for our configurator where we want to do random environments. So we're going to keep everything procedural, but just wanted to show you as an aside exactly how we can do that. So we'll come back to that in a second, but we've got our environment. Now we need a car model. So what we're going to use today is our McLaren W1. This is our latest Ultimate Series supercar. This is the successor to the F1 and the P1. The W1's been a great car to be a part of, and it's been great to see all the reception to that being launched. So what we're going to do is, we're just going to drop this into a blank scene. So we have our standard base model here. We've just dragged and dropped our FBX. Everything's been combined exactly as we need it for animation. We've got it ready to go, and then we just need to add some materials. So we have our materials set up and ready to go here. We've just dragged and dropped these in. For those of you who are not familiar, many of you will be, Epic do provide an automotive material pack. It's probably the best resource for getting started with visualization for cars. There is so much content in there. There's tons of body paints, caliper paints, tire materials, carbon fibers, metals, plastics, interior materials that you will need. Really, if you're new to this business, 100% recommend checking that out. We've essentially used that for quickness, and also we have some bespoke McLaren materials as well. So now once we've applied all our materials and things are looking good, we essentially now need to get this ready for animation. So we have this set up as a skeletal mesh, and what I mean by that is we basically have bones assigned to the geometry so that we can manipulate the car as we need to. So we can click on the main body, we can click on each of the wheels, and you can see the pivots moving as I jump around the model here. And this means we have control over different parts. You can see we can rotate the wheels. The calipers are moving here, but we'll correct this when we convert it into a control rig. But it means we have the main points of the car, only the 5 things we need, 4 wheels, and the main body allows us to do a standard animation. And it's great that now you can do this all in the editor itself. You don't need to do it in third-party software. You might have a preference. But if you want to do everything in UE, you are entirely able to do so. Now, you may also want to essentially do more there. You may want to add some more to the skeleton itself. What we can do is actually we can jump into our skeleton and edit it. This may be useful if you want to add more parts. You might want to animate some doors opening, for example. You might want to animate the rear wing deploying. And we can do all that just by right-clicking and adding a new bone in there. Now, for now, we're going to keep this simple. So we're going to keep it as just the main body itself and then the 4 wheels. But if you were to add something new, you need to make sure the geometry is paired to it. So each of these bones has polygons assigned to it. You can view this if you go into the edit weight setting. Now, if we jump in here, we can see the wireframe itself, and then we can select the different parts of the car and make sure the correct content is selected. So we have the main body, all the polygons are there, and then we also have the wheel itself. And we can jump around and make sure that's all set. One thing I would recommend, this side of the editor is quite heavy. This model here is probably about 20 to 30 million polygons. That runs incredibly slowly, probably takes all night to convert. So if you're new to this, maybe use either a decimated model, something more low poly to get to grips with it. Trying to select a single vertex in here, very difficult, takes a long time, can really get quite frustrating. But once it's set up, we essentially have everything good to go. Once we've done that, we can now convert it to a modular control rig. Now, there are kind of two ways you can do this right now. You can either use some nice third-party plugins to keep things nice and simple. It can basically take a skeletal mesh and convert it into Unreal's new control rig system. Or you can do this all in blueprints. Now, the blueprint process takes around 40, 50 minutes alone, so we're not going to show all that today. But we're going to post a follow-up blog post on Unreal's developer site on how we've done that exactly. But for now, we've basically used a plugin that will convert this. You might as well keep it simple if you're trying to save time. And this means our control rig is set up. We have our wheels spinning correctly. We have things moving when we need them to. We also have a bit more control over the suspension if we wanted to do that. But for now, we're good and we're ready to animate. OK, so we now have our car model and we have our procedural environment. We need to tie this all together. So basically, we want to show you how we can use this, not only for animation, but for our configurator as well. So jumping back to our forest scene, we've now added in a standard road. We've just used a fab asset for an American road texture, nice material that we drop into the scene on a plane, and then we need to jump into a nice camera angle. We've set this so that when we load in our car model, we can see the car in the correct kind of front three-quarter view, but also so we have enough view of the environment in the background, because that's the main thing that we're going to be changing. So we need to be able to see that and how it affects the car. So we'll drop our car model in here, and we've hooked it up to a level sequencer. Now, all we've done is just driven this straight down the road so that you've got a nice, simple animation. But right now, if we want to change the environment in the background, we have to click on every single volume and change the seed value manually. That's quite an involved process. We obviously don't want to have to do that every single time. So we could tie this up to an event so that whenever the animation sequence loops around, it calls an event and it refreshes the content. But that's going to be kind of difficult because if you're trying to render this out in real time, you don't want to see trees turning on and off. That makes things a little bit more difficult. So we decided to tie this up to our variant manager, which we'll use for our car configurator. So we're going to show you how we've done that now. So just jumping back out for a second, we now need to create a new blueprint class, which will have a custom event, and we'll show you how we have our randomization functionality. So what we're going to do here, we'll create a new blueprint, we'll jump in, and we'll basically do the functionality as I said. So once we've opened this up, we just need to add a new custom event. So if we right-click, add custom event, we'll give this a suitable name, and we'll just zoom in slightly. One thing to note, we need to set this to be able to be called in the editor. If not, it's only going to just work in a standard build. By taking call in editor, it means we can test it as much as we'd like. If not, things aren't going to work here. So we'll make sure that's ticked, and then we'll work on our actual custom event. So we're going to right-click here, and what we need to do is access all the volumes in the scene. So we're going to get all our PCG content just by searching for PCG volume. And then we need to grab each and every one and give it a random number so that it randomizes over time. So we're just going to loop through every single one. We'll tie it up to the array, and then we'll get each of our individual PCG actors. Now, before we generate new content, we need to clean up what's there before. So we're just going to search for a cleanup node here. And once we've done that, we have our target that we can access. Now, as I said before, changing the number of the seed value changes the random content that's going on. So we'll just set our seed here. So what we want to do is we're going to give it a random number. We're just going to give it a random integer between 0 and 1,000. That should give us enough variation so that we're never going to see the same environment twice. We've got 16 different volumes and 1,000 different possibilities for each one. Very unlikely we're going to see the same forest each time. So we'll just tie this up here. Don't judge me on how clean my blueprints are. We've definitely just not tidied this up too much, but we're keeping it quite simple. Essentially, now that we've hooked all that up, the last thing we need to do is just generate our new random content. So we'll add in our generate node here. And once we've done that, we'll set things up, we'll save it, and we're ready to go. So we'll just compile and save this. To take a little bit of a closer look at that, this is the PCG graph we have ourselves. So we have a new custom event. We're going to get all the actors in the scene, so basically all the volumes that we have. We'll then loop through each and every single one and access our PCG component. We'll give it a random number between 0 and 1,000, and then we'll basically generate our new content from there. Now that we've set that up, we now need to use this in our variant manager. Like I say, we're going to tie this to an extension of our configurator. Like I say, it's just a basic prototype that we've been working on, and we're going to just show you how we then link that up. One thing to bear in mind, if you're doing this, you need to make sure all your content can be accessed by your scripts. So by default, all PCG volumes in the scene can essentially, they are set to generate on load, so they're not going to be accessed by your blueprint, so we need to make sure they're set to generate on demand in the details panel. Once we have that set, we are then ready to tie things to our variant manager. So what we'll do now, we've just grabbed our randomized PCG blueprint, we'll drag and drop that into our scene. Now once we have this, we can open our new variant manager. We'll open this here. This is where we can vary the car. Sometimes we'll have different geometry, so we'll have different wheel options, different designs, different cars themselves, different body paints. We can vary this as much as we want. Today we're going to vary the environment. So we've got a button in here, and we're just going to drag and drop our blueprint. So all we need to do here is we're going to add a new function, and then we're just going to drag this out and make sure we select Create New Function, and that's going to open up a window for our event. So all we need to do here is, once again, give this a suitable name, keep it nice and tidy, and make sure we tick Call in Editor, so again, this can also be accessed. And we're just going to search for our custom event, and we'll make sure that is all hooked up and ready to go. So again, just drag this out, search for our PCG refresh, and then essentially that is all we need to tie this to our variant manager. So we're going to compile and save this, and then we're just going to move our variant manager over to one side so we can see a bit better. We'll just double check the correct function is synced up. And now we have it so that whenever we double click this, we can randomize the content in the scene. So we're basically varying everything, the seed value is changing, every single one of these, whenever we press this, will randomize. Now, once we've done this, it's back to our animation. So the environment in the background, we can now change this at the touch of a button, so it's now ready to randomize. So yeah, let's dive in. We have our car set up, driving down the street. We've got some nice lighting going on, and what's really great here, like I say, you can loop this as many times as possible. Whenever you click that button, you're basically going to have the environment changing in the background. Now, we can make this animation as long as we want. We've just set it to 15 seconds, and then we're changing things just to have a brief look. But again, you could make this more of an endless runner. You could extend it so it keeps going. But what's really nice here is we have our car, and it's great to just be able to evaluate it. The designers will also have the functionality to change their camera angles, view the car in 360 degrees. Again, it's an extension of our configurator. So everything we've brought before, we intend to then add this to our configurator ourselves. Now, having a nice little forest environment is all well and good, but we also want to be able to evaluate this in different scenarios. It's not always going to be a nice little sunny day. So, like I say, we've started with our clear sky environment. We've kept everything nice and sunny. It's good that you can see all the random trees in the background, but maybe we need something a bit more like some British weather like back home, so we can have a look at that. See the car in a different light, very quickly change the scene, allows us a different way to evaluate the car. We can also do different settings like some low visibility and fog, so you can see what the car will look like in there. And again, this is all running real time in Lumen as part of our configurator, and it can be basically animated out in real time, so we can render things out. We could switch this to Path Tracer for more views, but essentially now we can also view different lighting, so we can see it in an evening setting as well. And then one other thing we can do is we can swap out our assets. Now what's nice is this is the exact same car, the exact same level sequence, the exact same road. We haven't changed a thing. All we've changed is that random volume in the background. We've just given it some different 3D geometry. So we've just basically replaced our tree models with some boulders and rocks and some more debris again, just to make it feel like it's in the desert. And again, we've got an entirely random scene just from swapping something in a matter of minutes. Again, this gives us lots of different options for evaluating the car within. Now, Once we developed all that, we were super excited about it. We showed it to our designers. We thought this would be something really useful for the configurator. But we got quite excited about the possibilities of procedural content. And we thought, how much further can we take this? So one of the things we thought was, well, we now have infinite landscapes that we can then build things upon. And we thought, why not start simulating real-world environments? Even though we're doing things random, the real world can be random at times. But why don't we take real-world environments and see how PCG can help generate these? So essentially, what we did was, you can see here, for those of you familiar with racing, this is Eau Rouge from Spa in Belgium. The reason we've chosen this is for various different reasons. One, as a McLaren car, we need to evaluate it not on the road, but also on the track. These two things are both important when we're evaluating designs of our supercars. And we basically wanted an environment that we could use our PCG content on. So most modern racetracks can either be street circuits or lots of buildings going on. Whereas the nice thing in this Belgian track is that we have essentially, apart from a couple of grandstands, the track is just in the middle of the woods. It's got a forest, and we can use the existing content we've built. Like I say, when we're doing visualization, things can take weeks or months to get complete accuracy. If we wanted to get this track completely correct, we would have to either fly out there and scan it ourselves or get lots of visual references, and that would take a vast amount of time. But if we're trying to evaluate a car design in a couple of hours, we can use some PCG content and some procedural road generation to basically try that out. So this isn't supposed to be the world's most boring game of Spot the Difference. What we've done here is taken the track layout for Spa, and then we've converted that into Unreal Engine. All we've done is just copied in an image of the track itself, put a bit of transparency on it so we can see it, and then we've traced our splines around manually. So I basically took this in and traced some splines around the circuit itself. We didn't have access to the height data for Spa, so we didn't have access to a height map. That would have been great for the elevation. But like I said, this is something we're just trying to do quickly for some quick design reviews. So all we did was we watched a kind of point of view lap of someone driving around Spa-Francorchamps. So we could actually see the elevation, so see the high points of the track, see the low points, see where some of the turns were, and see how steep some of the corners were. By doing all of that, we can get a rough idea of the track layout. We can then basically use our spline and trace around the inside of the circuit. What's nice about that is once we've done that, we can load in our PCG volume. And we essentially have a racetrack with everything generating in the middle. It's a little bit difficult to see here, but what it's also doing, with a little bit more work to our blueprints, you can make the PCG follow the landscape itself. So the trees are actually going towards the correct height. They're rotating with the landscape. They're not sunk into the ground. We don't have to move everything manually. Like I say, what's super nice is we basically, from a couple different nodes, created our landscape itself in its entirety. And like I say, this is still work in progress, so we're still building upon this. We're still seeing the possibilities with it. But we can essentially jump to any part of the circuit and see how things are moving in the scene. So we have a live scene here. We've dropped the car in, and we can build upon this going more and more forward with it. So one of the things we could do is we could hook this up to an Xbox controller, so you can drive entirely around the track. That would take a bit more work. But the thing we can start to do is start to drop in some procedural assets again. So we can drop in some fencing, we can drop in some tire barriers, some gravel traps. And again, we can make this all with procedural content. We can just give it a small 3D model and then tell Unreal to just generate this round the spline curves and generate some things on the interior as well. Basically allowing us to now make as many tracks as we'd like. We can basically get the designers, ideally, to basically draw some tracks themselves, and Unreal will basically sketch them out so we can use them for evaluation. One other thing that we're looking to do going forward is basically be able to set up some cameras so that whenever we drop in some new car data for testing, we press render, it automatically rigs it up and drives around the entire circuit. Basically, then we don't have to do a single thing. We've dropped in some new data that's prepped, and we have a video already of a car driving around a track. Something that's incredibly useful for our design team and something that we hope to build going forward. So just to kind of recap some of that, as I said, we've got a basic PCG volume that we've built here. Again, from taking two little tree assets, we've built an entire forest environment. And then we've taken our W1 model here, so we've taken an animated car sequence. We've had the car essentially driving down the track itself, and then it's good to go. And we can build upon that, we can make the landscape vary, and we can change the content as much as we like. And this is where we end up. So we've got a new extension of our configurator. We have a random scene. And again, this is something we can build upon. It's very much in the prototype stage. It's something that we just thought of quickly. I do have to quickly say thanks to Dan Howe and Jack Griffiths and the Viz team. They were really fundamental in helping me pull this together. It was great support from them. And yeah, it's been really cool to pull this together, and we hopefully will be able to build upon this and use it for further testing. But yeah, hopefully you found that a nice little insight into some of the prototyping we do at McLaren. Happy to take any questions.